So good morning, everyone. Hope you had a good day yesterday and a good hackathon so far. Hello. So yeah, first thing, so I would like to thank Anthony, Julie, and the whole team for having me in this hackathon. I think it's really a good idea to have this kind of hackathon to, let people learn about all these tools, which are kind of crucial if you want to let others use your software. So it's really a great initiative. Yeah, just a couple of words. You've seen we're using Big Blue Button, so I'm also very thankful to Anthony and Julie and everyone for letting us use Big Blue Button for this session. I kind of insisted on it because, well, the Zoom has privacy issues. It kind of forces you to install spyware. So I felt like, yeah, I don't want to do that, right? So we're using Big Blue Button. I hope it works well. It usually works well for me anyway, but if you have any problems, do let us know. All right. So today, I'm going to talk about reproducible software deployment with GNU-Guix, which is a package manager. I'm going to talk about theory, so to speak, but also about packaging, because you've done very concrete hands-on sessions so far, and you've learned very concrete tools. So I also want to go into the concrete details of all this. So I try to do that. Yeah. There's a picture of a crowd holding packages. It's an all-man crowd. We can achieve more diversity, I guess, in reality. I hope so. A little bit about my background. So I work as a research engineer at INRIA, which is the French Research Institute in Computer Science. I work these days primarily on the development of Guix for high-performance computing, HPC, and for reproducible research, as we will see. And I also work in a department that takes care of providing training sessions and things like that for scientists at INRIA. So we're very much in line with what's being done with this hackathon. Again, trying to tell about good practices in terms of development and publishing software and all that. All right. So where's my cursor? So just I will start by giving a little bit of background about Guix and why you should care and why it differs perhaps from other kinds of tools in this area, other package managers. You will actually learn about other package managers later on today, so you would see. I guess you're well aware of the so-called reproducibility crisis in research. So there have been a number of high-profile issues with non-reproducible research articles, for example. And over the years, over the last decade, I would say, societies, publishers, etc., have been trying to improve the situation. For example, by having badges like this one. So the one that's displayed here is the artifacts evaluated badge or functional artifact badge by the ACM, which is the Association for Computer Machinery. So that's the kind of badges that they provide for papers in computer science. I suppose in chemistry you have similar kinds of badges. I know the IEEE also has a badge system that's kind of the same thing as the ACM one. So you've probably seen that before. And of course, providing reproducible research is a lot of work. It touches many different areas, but one of them is software deployment, and that's something that's often overlooked. If you're not able to first deploy your software in a reproducible fashion, then all the computational experiments that you do afterwards, all the the number crunching application that you have are not going to be reproducible, and that's a problem. So the Grail, in a way, is initiatives like the Rescience Journal, which was started by colleagues of mine. There are many initiatives, but this one is the one I'm the most familiar with, and I think it's very interesting So the idea here is to reproduce results that that were published in papers before, right? So people would take a paper, read it, and try to replicate the results that appear in that paper. And to do that, they go pretty far, actually. Usually that means re-implementing the computational methods that appear in the paper. So most of these papers are currently in neuroscience, but it's applicable to other fields, obviously. The goal here is to, well, to strengthen scientific results, right? If we're able to replicate results, then that's a very good sign. So it goes pretty far. So if we look at the big picture of reproducible research, we have at one end what I would call the Grail, which is initiatives like the Rescience Journal, which go very far to replicate research results. And at the other end of the spectrum, we have initiatives like software heritage and also things like the Zenodo. So I don't know if you're familiar with software heritage. If you're not, it's a project that aims to archive all the source code, all the public source code that's available on Earth, basically, and in particular, scientific source code. But really everything, because there's, you can't make a distinction. So it's a very ambitious project, and they've been ingesting source code from many different sources, like commercial hosting sites like GitHub, GitLab, package repositories like the Python package index, PyPy, CRUN, etc., etc. So they have billions of repositories, and it's just, it sounds like without this, we cannot actually do the rest of what we want to achieve in terms of reproducible research. We first need to make sure that our source code remains available if we want to make sure that eventually we can reproduce computational results. And so these are the two ends of the spectrum. On one end, we have the journal that reproduces, replicates results, and on the other hand, we have the archival, so the fact that we archive software, and of course there's also Zenodo, for example, which archives data. So we need to have all these things. And in the middle, we need something, right? So we have source code on the left, but we need to be able to take that source code and somehow turn it into actual software that you can run, so we can eventually reproduce results pretty much in the way that Rescience does it. And this is where Guix comes in. So our goal is to, to allow you to take source code and to redeploy it, even if it's months later, even if it's on a different machine, and so on and so forth. Right. So I hear you've been working a lot on build systems over the last few days. Now what? Oh, and I should say you can feel free to interrupt me during the talk. I don't mind if you have any questions. And you can also ask questions at the end, but you can interrupt me. Right, so I hear that you've been working on build systems. So now you have hopefully software that your colleagues and even people you don't even know can install from source, right? So you have a CMake or an AutoTools build systems. And that's good, but what's the next step? So, at this point, hopefully people can take your software and run configure, make install, or CMake something, make install, right? And that's already a very important first step. If people, if you want to allow people to actually use your software, that's crucial. That's a crucial part. But people are lazy, and very often we want to, to have a very fast installation method, right? We don't necessarily want to build from source and to run CMake, make install by ourselves. So people usually tend to resort to, higher level, easier methods to install their software. So what do we have? So if you've used HPC, high performance computing clusters, you've probably seen modules before. So environment modules, that's a very old piece of software, but that's very convenient. So typically you would run module load some software, some version, and it would modify your environment variable so that you get that software in your environment. So for example, module load GCC and you get GCC available in your shell. And it's very convenient because it allows you to to switch between different versions, different implementations of, for example, if you choose MPI, the message passing interface, you can choose between different MPI implementations and so on and so forth. So it's very convenient as a user. But you've probably noticed that these modules differ from one machine to another. Like if you go on one cluster, you may have a module that's called GCC 7.5, but on another cluster, it's going to be called differently. And that's not convenient. And that's because fundamentally, system administrators have to actually build from source all these packages, right? And to make them available as modules. So that's a very manual process that sysadmins have to go through. And it's non-portable. So if you go from one machine to another, or even if you remain on the same cluster, but you come back 6 months later, perhaps some modules disappeared, perhaps they are still available, but they are different, like, they are built differently with different options, different flags, and so it does not provide you any kind of reproducibility.
Sorry to interrupt you, Ludovic.
Yep.
I think I'm hearing some echo from, maybe it's from Anthony.
Some echo from Anthony, you mean? All right. Maybe
there's still an echo.
For me, it's actually fine. So.
Okay.
For me, it's fine too.
Yes, I'm here. No echo.
Okay, good. Well.
Okay, thank you for acknowledging that. Okay, you may continue. Please be informed that we are also broadcasting using the Zoom link.
Okay. Okay, well, thank you. Well, let me know if there's echo coming back later. All right, so this is modules, right? So it has some shortcomings in terms of reproducibility and even in terms of the amount of work that sysadmins have to go through. So you've probably heard about package managers, and you're definitely going to hear about them today. People have come up with different solutions to that to provide the same level of flexibility that you have with modules, while also providing automation and sharing among clusters. So package managers are not a new thing. If you've used GNU Linux before, if you've used Debian, for example, Ubuntu, Fedora, and all that, they all have package managers already, like apt for Debian, RPM, yum, and so on. But these package managers can only be used by the system administrator. So it's not convenient on a cluster. As you can imagine, you cannot let everyone run those tools. And so that's why people started developing a package manager that you would use on top of these existing distribution. So for example, Spack, Conda, EasyBuild, these are package managers that you would install on top of a running Linux system. And instead of using apt, for example, RPM, yum, you would use directly Spack, Conda, EasyBuild to install software on top of that system. So that it's being pretty much used on HPC cluster these days because it's convenient. It automates the whole process of installing software. So basically, it runs, CMake, make install for you. It knows about the dependencies among the packages. So you can easily deploy a whole software stack using these tools. So it's really a great step forward. Yeah, it does have some limitations though. So because these tools rely on an existing distribution, right? And they're meant to be used on top of a Linux system that already provides a number of software packages. And because of that, they make some assumptions, implicit assumption that, let's say, for example, you have some version of GCC available, some version of a C++ compiler, some version of the binutils, the binary utilities. And if those assumptions are not met for some reason, then things might go wrong, perhaps they'll be fine, but perhaps you'll get a runtime error, or perhaps it won't even build, right? So for example, you would run Spack install foo, and instead of actually building that thing, it would fail because you don't have the right version of the C compiler available or something like that. Yeah, so this is a snapshot from the Spack GitHub project, for example, with all the issues tagged with build error. Yeah, I'm bad-mouthing a little bit about these tools, but they're they're fine tools. But you'll hear about Conda and Spack later on today, so you'll see what these people say.
Are they all free, or are these tools all free, open source, or are these commercial tools?
So these three tools are free software, so open source software if you want. So yeah, you can download them from the internet, and it's pretty easy to use, right? They do provide non-free software though, so proprietary software. But I get back to that later. Right. So yeah, same with Conda. So Conda, if you've never used it, it's used quite a lot in bioinfo in particular, and well, in many scientific places, I guess. But again, it's not ideal in terms of reproducing environments later, because fundamentally all these tools, Spack, Conda, EasyBuild, rely on the fact that there's already software available on the system underneath. So if you change the software that's underneath, then it's not going to work. Yeah, so that's one of the problems that we have. So a great step forward, but still shortcomings in terms of reproducibility, or even just in terms of being able to build and deploy the same software everywhere. So how do we solve that? So you've probably heard about containers. I think you heard about containers on day 3 of the hackathon, right? Is it a solution? So by containers, I mean tools like Docker, Singularity, and so on and so forth. So the big issue I see with containers is that they lack transparency. So a friend of mine likes to say, it's like a smoothie. You can easily tell whether it's to your taste, whether you like it or not. But it's a bit hard to tell just by looking at it what's inside of it. Is it whale oil? Is it strawberry? You don't know. And that's a bit of the same story with containers. Containers are about building images, one big Docker image, for example, that contains all your software stack. So it contains, let's say, your application, the one that you're interested in, plus everything it depends on. So that's a whole big software stack. As someone who received that big image of 1, 2, 3 gigabytes, it's very hard to tell what's inside of it, and it's nearly impossible to reproduce that image to get to the same image. So you don't really know what you're running. So it's very convenient because it allows you to make sure you're running exactly the same piece of software, because you have the bits of the software that you're running, right? So if you're sending the image, it's a bit as if you were sending your machine, right? You take your laptop, you know that your software works on your laptop, you take it, you send it by mail to your colleague, and then your colleague is able to run the same software, right? Because you have everything in there. So that's very convenient in terms of being able to reproduce exactly the same thing. But the downside that you don't really know what you're running, right? You cannot verify what's inside of it, and you cannot reproduce it. So for example, I think you've seen about Docker yesterday. This is a dev file for Singularity, which is another container tool used in HPC. It's very similar to Docker in spirit. So in Docker, you have Docker files where you specify, steps to create an image. And in Singularity, you have so-called dev files where you also specify steps to reproduce the image. So usually those steps, they start by, you have that from line, both in Docker files and in dev files. That from line says, okay, we'll start from an existing image, right? So the from line here says we'll start from Ubuntu 18.04, which is already a very big image, like, I don't know, 1-2 gigabytes. And from there, we'll run a number of steps to actually install the software that I'm interested in to produce the image, right? And typically those steps include apt-get update, for example, which means let's first update the list of available packages. And from that updated list of packages, we'll install, in this example, Netcat. And that's kind of a problem, because if you run that dev file to produce an image today, you're not going to get the same result as if you run it 6 months from now, right? Because by then, the list of available packages to APT will be different than from now, right? So maybe you'll get just a newer version of Netcat, or maybe you'll get different things. You can't really tell, right? So this recipe that we have here to produce the container image is not reproducible, and that also means it's not verifiable. Yes, someone is raising their hands. Yes, please.
Hi. So I had this exact question yesterday, day before yesterday, and one of the solutions was that you could avoid using apt-get and install all the software from source. Then you have exact control of what software. So is that viable option, or is that not really possible?
Right. Well, then it becomes a bit more complicated for you. If you have to describe how to install the software from source, it can be tedious, right? But that would be an improvement, I guess. Now, the issue that you would first need to fetch that software, that source code, right? And that step also needs to be reproducible, ideally. So it's never going to be ideal. And there's also the fact that you still have that from line, right? Which means you're taking a whole lot of pre-built binaries to start with, and those remain unverifiable. You don't know how to reproduce them. So it's not, it's never going to be really ideal. You cannot easily inspect the whole thing.
Okay.
Right? Yeah. And that's the last thing. So it's not reproducible, and it's not easily inspectable. Like, it's very hard to tell what's inside the image. Even if you fully trust whoever provided you with the image, it's very hard to say exactly which pieces of software are in the image, how they were built, what compilation flags were used, what config flags were used, and so on and so forth. So, not great. Which brings me at last to Guix-HPC. So Guix is about trying to address the issues, and in the Guix-HPC effort, we're trying specifically to focus on all these reproducible research issues and also on use cases for high performance computing. So Guix itself, as a project, started in almost 10 years ago, and today it provides about 20,000 packages, all free software, which means in Guix proper, you do not get any proprietary software. That's a policy decision we made early. I think you cannot really do reproducible research if you're relying on proprietary software, because these are black boxes. You don't know what they are doing, so that's not a scientific method, right? So I do understand that sometimes people, have to rely on non-free software, in particular for monopolies like GPUs, where many people use CUDA, for example. So the tool itself, doesn't care. It just manages packages, right? So people developed separate channels where they have all the software they need, whether free or non-free. So everything is possible. It supports different architectures, and the Guix-HPC effort itself, which focuses specifically on reproducible research and high-performance computing, was started with different research institutes back in 2017. All right, so what does it look like? So if you've ever used a package manager before, like APT or whatever, Guix has a very similar interface, right? So you can run Guix install and the list of packages and just install them. A key difference here is that it does that without requiring root privileges. So even as a normal user, you can run Guix install, which is pretty cool. And when you install software, you don't install it globally for all the users of the system. If it's a multi-user system, you just install it for yourself in what we call a profile, which is your own personal profile. So on a cluster, that means that you can have one user running GCC 7, for example, having installed GCC 7 in their profile. And on the same cluster, you can have a different user who has installed GCC 11 in their own profile. And there are no conflicts, right? But still, if you have many users on the cluster installing, GCC 11, for example, then that's okay. There's no duplication. GCC 11 is going to be stored only once on the cluster, so you're not wasting space and so on and so forth. So the second line that we see here allows Guix to tell you about the environment variable that you need to set to actually use the software that you've installed. So for example, in this case, we've installed GCC plus OpenMPI, which is a C library, plus HWLock, which is also a C library. And if you're going to use these things together, then you probably need to set a number of environment variables like path first, and cpath, the search path for C headers, and library path, the search path for libraries. Things like that. So Guix knows about this, and if you run that command here that we see with Guix package search path, it will automatically define those variables. Another thing that's unusual compared to other package managers is that when you install software, you upgrade software, and so on and so forth, it's always a transaction. So you can always roll back to the previous state. So for example, the usual case is you upgrade your software, and something breaks, you don't know why, but you have a deadline, and so you're not going to investigate right away. So you can roll back, and you're exactly back in the same state as before, so you can just continue doing your thing without worrying. And that's a very nice safety net to have. It really changes how you approach things. The last command that we see here, Guix environment, is more like a virtual env in Python, if you've used that before. So it creates some sort of a virtual environment. In this case, it will launch a shell that contains GCC toolchain 5.5 plus HWLock 1, version 1, right? So it's an easy way to try out software, for example, without actually installing it in your profile. So it's like you're creating on the fly a shell that will contain just the packages that you've asked for. So this is another way to use Guix. There are many ways to use Guix. I'm just showing you the main ones. So before, we were running a Guix install, for example, which is the kind of the classical way of doing it. But you can also declare in a file all the packages that you want to install. So instead of running a number of Guix install commands, you can create a file that contains what we call a manifest, which is essentially a list of packages that you want to install. So in this case, I'm creating that file called mypackages.scm that contains the snippet that we see below. Specifications to manifest GCC toolchain, OpenMPI, Scotch mumps. Basically, it's telling you, I want to have these 4 packages installed. And so when you run the command Guix package -- manifest mypackages.scm, it automatically installs exactly those 4 packages and nothing else. So that's pretty convenient because you can share that file with colleagues of yours. You can store it in version control. So it makes it much easier to work with other people, basically, or for yourself, even if you want to reproduce your environment later. But as you can see, we're not specifying any version here, right? So if I run it today, I will get a result that's different from what happens if I run it 6 months from now, for example, because 6 months from now, GCC will be at version 12, 13, I don't know, whereas today it's GCC 11. So we're still missing something if we want to reproduce the exact same environment. And so what we're missing, the information we are missing is the exact revision of Guix that we're using. So you have to think of Guix as both the tool, the command line tool, and the set of packages. Which means that if you capture the revision number of Guix that you're using, then you know exactly which package versions it provides. And so if you run Guix describe, you get the commit ID of the Guix that you're currently using. And so if we have Bob on their laptop who has that mypackages.scm file, plus they run Guix describe, and from there they can send that information to Alice, and Alice on their supercomputer can run Guix pool -- commit equals to that commit of Bob, and that will bring Alice at the same Guix revision as Bob. And from there, Alice can actually run Guix package -- manifest, and they will deploy the exact same packages as Bob, right? So we have different people in different machines, and they're deploying the exact same thing, bit for bit. Which is pretty good. Like if you're working on a paper, you want to go back to it years later or a month later, that's always possible, right? You just need to capture that information. Yes?
Can I quickly ask something? So just to understand, so where are all the specific versions of all of the packages that were installed on Bob's laptop saved? And so this, because what's also not quite clear to me, is this now a commit hash of the Guix software, or is this a commit hash that somehow includes all of the environment?
So the commit ID that we see here that Guix describe shows is the commit ID of the Guix revision that you're using. And Guix itself, it's stored in a Git repository, and it includes not only the tools, but also the package definitions, right? And so at any given point in time, Guix provides, package definitions for GCC, Python, whatever. Usually it provides only one version of each package at a given point in time, except for some packages like GCC Python, for example, because these are packages where it's useful to be able to choose between one version or the other. But if you take, I don't know, Emacs, for example, there's one version available at one point in time, right? Or if you take, for most libraries, for example, there's just one version available at one point in time.
I see. No, thanks. That makes a lot of sense now.
Right.
Just one quick question, a follow-up question then. So what if, I don't know, this Guix version does not support the hardware that I have in 5 years, and so I have to go back to some old version of Guix to get exactly the same environment?
Like what if you switch to a new version that does not support your new hardware or something like that?
Yeah, just to say that, let's say now in 5 years I want to reproduce my environment, but for some reason, so the thing is now it means I would need to use the Guix version of today, right?
Yes.
For example. But how can one guarantee that I can still build this, for example, on my hardware?
So we can guarantee, like, for example, if the Intel x86-64 architecture disappears overnight, then we don't know what will happen. So we don't provide that kind of guarantee. But most software packages are actually portable, and Guix itself supports different architectures already. So like if you stick to Intel architectures, for example, chances are that you will be able to redeploy the same piece of software, years later, because it's not disappearing, as far as I know.
I see.
But yeah.
Exactly. I guess what my question was more I was a bit surprised that this commit hash includes not only kind of the catalog that you have at that point in time, but it also includes the Guix software as well. But I guess your point is that they're somehow so intertwined that one should have the same of both.
Right. Yeah, it can be kind of surprising that it's not the commit of just the catalog of packages, but instead the commit of everything. But yeah, everything is really, it all works together, right? So it just, that's how it is.
Okay, thanks.
So this is just to say that Guix allows you to travel both in space and time. And here's a reference to a movie that people old like me might remember. So it allows you to travel in space, like you can deploy the exact same piece of software bit for bit on different machines. And in time, because you can reproduce the exact same thing months later, years later. And so because, in talks and everything, we would often talk about this, make the analogy with this time machine. So eventually someone obviously came up with a time machine command for Guix. And so you can use time machine to do two things at once. So you say, for example, Guix time machine -- commit, and you specify the Guix revision, and then you specify the Guix operation that you want to make. So install hello, for example. And so you can, in a single command, move back to a specific revision of Guix and, for example, install a package. That's pretty convenient in practice. It's not just for fun.
I have a question.
Yes?
Yeah. When you say, I'm not sure I understand if you're installing binaries or if you're building from sources here, because you said you reproduce bit by bit.
I'm getting there, but I see we're getting late, so maybe I should hurry up a little bit. I'm getting there. So we're actually building from source, and this is an example package definition. So everything happens as if you're building from source, but as in Gen 2 if you want, but since you don't want to wait forever, like if you're installing packages, big packages like, I don't know, LibreOffice, for example, Firefox, we are providing a way to use pre-built binaries, right? But it's just an optimization. So those pre-built binaries are verifiable. You can choose to opt in. By default, it's enabled. You opt in to get pre-built binaries from the official project build farm. But you can also, if you don't trust the build farm, for example, you can say, I'm going to build everything from source locally. And Guix knows how to build things from source, right? So fundamentally, Guix is source-based distribution, if you want. It knows how to build software, but it can optionally use pre-built binaries if you allow, it to use binaries from some server, which is very convenient. So this is a package definition, for example, from a solver that's developed at my workplace at INRIA. So here you can see we're defining a package with, we specify its source, and its source is a Git checkout, and we specify the Git commit here. So when I was talking about traveling back in time, you can already see that there could be a problem here. So for example, what happens if gitlab.inria.fr disappears, and I want to reproduce that software environment. I want to be able to reinstall Pastix. Well, we could have a problem, right? And that's where software heritage comes in. So I mentioned it at the beginning of the talk. Software heritage, is a universal archive of public software available. And so when Guix fails to fetch software from its original upstream URL, it will automatically fall back to fetching it from software heritage, which means you have the guarantee, or at least that's the goal. We're still working on it. You can read the article below for more details. But the thing is, we want to guarantee that all the software that Guix refers to will remain available forever via software heritage. And that's the thing. So you can always fetch a source via software heritage. All right, so getting more into concrete issues. So Guix itself is not as popular as Conda, for example, but you can find it on a number of clusters. So in particular, clusters in France. We have people doing bioinfo in Germany, in the Netherlands, and in the US also, running Guix directly on their clusters. So it's ideal when you're using their clusters because you can directly type Guix foobar, Guix pull, Guix install. It's very convenient. But what do you do when you go to a cluster that doesn't have Guix or doesn't yet have Guix? Well, we have a tool called Spack, which allows you to create an archive, a self-contained archive containing the packages that you ask for. So in this example, I'm asking for Python, NumPy, SciPy, and it will create a tarball, a tar.gz archive containing these 3 packages and all their dependencies. So I can take that tarball on a machine that does not run Guix. I can unpack it and run Python and NumPy and SciPy from there. It's more convenient if you use -- relocatable or -- relocatable, because that creates a relocatable archive, which means that you can extract that tarball anywhere on the file system, and from there you can run /bin/python without having root privileges or anything. You know, you can unpack that tarball anywhere on the file system, and that makes a big difference. Or if you're targeting a machine that has Singularity available, so the container runtime, you can also create an image in that format. So you just say Guix-Spack -- format equals to squashfs. That's the format that Singularity uses, and it creates an image in that format that you can use directly with Singularity run. Or again, if you're targeting a machine that runs Docker, you can also create an image in the Docker format. So it might sound kind of ironic, given that I said bad things about containers before, container images. But the key difference here is that the way we're producing the container image is reproducible, and we have provenance tracking and everything. So if you look at Docker, for example, Docker is really 2 things. There's the tool that produces images, Docker build, and then there's the container runtime, so the thing that allows you to run those images. And what I'm critical about is really the tool that produces images, Docker files, right? Whereas the container runtime itself, Docker run, it's convenient, you know, it just does a job. And so what we're changing here, that we're using Guix-Spack to produce the image, so we're keeping it reproducible, verifiable, and with proper provenance tracking. All right, and Guix allows you, so you know, in HPC people like to tweak software, you know, they like to change how they compile software, how everything is built, you know, the options and everything. So you can specify package transformations, as we call them, to change, for example, to replace a dependency Scotch by another PT Scotch in the second example. All right, I see it's already 9:45, so I'll be very quick. How to get your first package done?
Ludovic, just if you need more time, just take the time you need. Don't try to go too fast.
All right. Sorry, try to not go too fast. Then we can go until 10, maybe, or
yes, no problem, no problem.
Okay, all right. I speak too much. I'm sorry. So your first package. So because in the previous days you've hopefully been able to turn your software into something that's installable from source by anyone by running cmake or configure. Now the next step for you is to actually write a package. So either for Guix or for Spack or Conda, which you'll see later on today. And so I wanted to show you concretely how you would go about doing that for Guix. So for Guix, the first step is obviously to install Guix. So you can install Guix on top of your GNU Linux distribution. So if you have a Linux machine, a laptop, anything, you can download it from the web page above here. And you can install it on top of your distribution. It's not going to break anything, you know, it's just an additional way to install packages, but it's not going to overwrite, for example, what's already available in /usr, things like that. You know, it's just it just lives its own life separately. So no risk. And there's if you go to the web page, there's a binary installation script there that will automatically download Guix prebuilt binary and verify its signature, install it, blah blah blah. So it's pretty easy, and in 5 minutes you should be done. Right, so the next step would be to create a Git repo to contain your package definitions. So in Guix parlance, we call that a channel. So a channel is basically a repository that contains several package definitions. Second step, you would write or generate your package definition. Then you would test it with Guix build. Usually, I won't lie, it takes several iterations. No matter which tool we're using, actually, it takes several iterations to actually make sure that your package builds correctly. And finally, you would commit your file, push, and enjoy. And optionally, Guix allows you to publish pre-built binaries with Guix Publish. So over HTTP, you can make pre-built binaries available. That's very convenient. Like if you want your colleagues to be able to install your software without having it built from source locally, that's convenient. That's faster. So I said you can generate your package definition in some cases. So for example, if you have a package that's on PyPy, the Python package index, or if it's on CRAN, for the R repository, then Guix import can automatically import that package and convert it into a Guix package, basically. So if you're in one of these cases, that's great. But if you're using a typical C, C++ Fortran package that's written in using CMake or AutoTools, then you probably need to write it by yourself. All right, so what does a package look like? So this is a package definition in Guix. You'll see similar things with other tools. So basically, if you look at Spack, you have something that's quite similar, except it has a Python syntax instead of this S expression scheme style. So this is a scheme programming language, which is a variant of Lisp, but you don't need to be a Lisp programmer, to understand what's going on here, because it's pretty declarative, right? So what do we see here? So there's a bunch of things. So we have the package name, its version, and so on and so forth. The source field, as you can see, tells us where we're getting the source. So we're using string append to build the URL. We're fetching hello-1.0.tar.gz, and here we're specifying the expected SHA-256 hash of that tarball. So how do we obtain that hash? Well, by running the Guix hash command. So if your source code is in a tarball, you just run Guix hash hello-1.0.tar.gz, and it prints the SHA-256 hash, and then you just need to paste it in your package definition. All right. So that's an important bit because that guarantees reproducibility, right? If for some reason example.org eventually publishes a different file, then Guix will refuse to build it because it will say, hey, look, I'm getting a different file. It doesn't have the right hash, so I'm stopping here. That's a very important property. The build system thing here is telling Guix how to build the package. So in this case, if you say GNU build system, it means it's going to run configure, make install. But it also says that the package implicitly depends on GCC, make, bash, binutils, glibc, and so on and so forth, right? The standard dependencies. And of course, you can choose a different build system. So you can choose CMake build system instead. And that means that Guix will run CMake, make install, and so on and so forth. What else do we have here? So here I was showing a simple package without any dependencies other than GCC and everything. But if you want to specify additional dependencies, this is how you would do it. So you add an input field, and in that inputs fields you have pairs of labels and packages. So OpenMPI, PETSI in this example, and so these are the dependencies. And here we have that comma OpenMPI comma PETSI, which are actually references to variables, to other variables that define those packages. So in this example, we're defining a variable that's called hello TREX, but you can imagine there's somewhere a variable that's defined in the very same way for OpenMPI and one for PETSI and so on and so forth. So that's my package definition. And from there, you know, if you're just using CMake the right way, Guix is going to be able to build your package directly, and that's it. And so that's why it's important to have a good build system in the first, as a first step, because if you're using CMake or AutoTools correctly for your package, then Guix and Spack and other package managers are going to be able to build your package very easily. Yes.
Yes. So where does it say what CMake version there is? What is the compiler?
So this is not explicit here. It's provided by the CMake build system thing that we see here. But you can, like, if you need a specific CMake version for your package, you can specify additional arguments for the build system. So you can add an arguments field that says CMake that version. So there's a few versions of CMake available in Guix proper, so you can choose from one of these basically.
Maybe as
and
a
the
quick
compiler.
And the compiler, right? So the compiler is also it's bundled as part of the build system, so you don't see it here. But if you use, for example, Guix graph, there's a Guix graph command that allows you to display the dependency graph of a package, and so you can see which version is being used. So it's by default, all the packages are built with the same GCC version, which is currently GCC 7.5, and it's about to change to GCC 10, I think. And if you need a different version, you can explicitly add it as part of your inputs.
Maybe a quick follow-up. So is it then also kind of a bit of a different philosophy in specifying the dependencies? So that is it often the case that you don't specify version ranges, and so that you get these version ranges implicitly through the kind of the Git hash of the Guix at that time? Or?
Yes, that's a very good question. So it's a very different philosophy if you compare to, for example, Spack, or I think Conda does that too. So, for example, in Spack, package definitions provide a lot of degrees of freedom, right? You say, I need some OpenMPI, you know, you don't say exactly which one, or maybe you specify constraints or like version ranges, right? But this is very different in Guix because all those package definitions defined one graph, you know, one dependency graph with precisely one version of Hello TREX, for example, one that depends on a specific version of OpenMPI, that depends on a specific version of glibc, for example, and so on and so forth. So there are 0 degrees of freedom in Guix in that sense, right? So you're really specifying everything precisely. And you know, we like to focus on version numbers, but version numbers are just part of the story. So for example, OpenMPI has, you know, a ton of configure flags that change significantly how it's going to behave, or it has a ton of optional dependencies that change how it's going to behave. So in Guix, instead of focusing on version strings, which are not, you know, that meaningful, we precisely define the whole dependency graph. And for example, here you can be sure that your package is depending on OpenMPI that is built in that particular way with those specific configure flags and those specific optional dependencies.
Thanks.
Yes, we have another question here. Yeah, another question or no? Someone raise their hand. Okay, well, just continue. All right, so this is our package definition. So you would store that in a file, but we need a little bit of boilerplate on top of that. So typically you would, so in one file you can provide several package definitions. And so you need to start that file by a module definition, which is sort of like a library in in other languages. And so you would say define module TREX, for example, and then you specify a bunch of modules that you need to actually for your package definition. So for example, you need the Guix module, you need the Guix build system CMake module because you're using CMake build system, and you need the licenses module for your license field at the bottom. And so, yeah, this is for a file that's called trex.scm. So the module name has to match the file name, right? So if you call your file trex.scm, you have to call your module trex. And if you call your file trex/hello.scm, then you have to call your module trex space hello. And this is it. So once you have that package definition with the module boilerplate at the top, you can actually test it, right? So how do you do that? So you would use Guix build, and you need to tell Guix build where to find your additional package definition, because by default it just cannot guess where hello TREX is. So you need to say, let's assume that you've put your package definition in /source/TREX. Then you would say Guix build -l /source/TREX hello TREX. And at this point, it should be able to load your file and to find the hello TREX package definition. And so maybe the first time you'll run it, you'll get a message like this: OpenMPI unbound variable. Did you forget to use the GNU packages MPI module? Yes, maybe we did. So you would, add the #use module GNU packages MPI form, to the boilerplate at the top, so that the OpenMPI package is found. You save your file and you rebuild, and it will start building it from source, and eventually it will just print that one line that we see at the bottom, which means that it succeeded, and the result of that build is available in that directory, GNU store blah 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 hello TREX 1.0. So basically, every time you build a package with Guix, it ends up in one new directory in that GNU store directory. And so from there, if it builds on your machine, it's going to build on someone else's machine, even if they have, for example, even if your machine is running Ubuntu plus Guix, and that other person's machine is running CentOS plus Guix. It's just going to be fine, because the Guix packages are self-contained. They do not rely at all on what's available on the machine outside of Guix. And from there, you can already do a number of things. So you can run Guix install if you want to install your package. You can run Guix environment if you want to get a development environment. You can run Spack if you want to create an image of your package. And the last steps would be to publish your Git repository, just like you would do with any Git repo. And then users who want to use your package would need to specify an additional channel in their config file, in their config Guix channels.scm file. Using this snippet, basically you say, I want to append this list of one channel to the default Guix channels. And from there, they can run Guix pull, and that will give them your channel in addition to the default channels. And they can install hello TREX from there. Okay, I went a bit fast, but there's a lot of documentation and material that you can get from the Guix website. And in particular, in the manual, there's a section that's called Defining Packages. So it should answer lots of questions for things where I went too fast. Yes, we have one question from Otto. Yes, please. And Anthony, who wants to speak? Otto? You want to say something? Or Anthony?
Okay, so I will ask you a question.
Okay, go ahead.
It's about the glibc, because usually when I try to compile a statically built binary and move it on another machine, I sometimes have the problem that the version of glibc is not correct, and even my static binary doesn't work. So is the glibc also stored inside the Guix package, or how do you handle this?
Yes. So like I said, the Guix packages are self-contained. So if you look at the dependency graph of your package in Guix, it goes down to the bottom, including glibc. And so Guix comes with its own glibc. It doesn't use any package that's installed on your system outside of Guix. Nothing at all. So you can be sure that if it works on one machine, it's going to work on another because it doesn't depend on any external state, right?
Yes.
Yes, Leopold.
Oh, yes, sorry.
Oh.
Thanks. I mean, if you want to continue quickly, Anthony, go ahead. I mean,
no, I had a question about something else. Another question, so I'll come back.
Okay. Thanks a lot for the introduction. I mean, I was like a little bit aware of Guix and Nix, but not to a deep level. And I have many questions, but I don't think we have time for it. I will send some of them maybe per email. But one that's maybe interesting for others as well is what is the key difference to Nix from an HPC perspective? And then maybe another one would be, is there a registry of Guix channels? So how do I find out about all of the other Guix channels that are out there?
Yes, so the difference to Nix, so there's technical differences and there's non-technical differences. So technical differences is that, so similarities first, Guix and Nix are both using the same functional model that Nix pioneered. And so some of the things I described here also apply to Nix because it's a functional model and they are very similar in that spirit. The technical differences are that, well, if you look at package definition in Guix, they're very different from those in Nix. Some like it better. The command line tools are different. I think they're easier to use in Guix. I'm saying this because I contributed to Nix before, but that was a long time ago. So I also know that Nix has been evolving a lot since. There's probably better integration still in Guix, for example, things like Spack. You don't have them out of the box in Nix. So some things are easier to use. You have also package transformation options in Guix that allow you to change the dependency graph right from the command line. So that gives a lot of flexibility, and you don't have that in Nix proper, not as easily at least. So there are a number of differences, and also for less technical differences, we have we like to focus on building everything from source in Guix. So in particular, we are part of the reproducible builds and bootstrappable builds efforts, which means that we try hard to build everything from source to obtain the maximum level of transparency and provenance tracking, which is quite different in Nix, I think. And that's it. And regarding channels, so if you go to the hpc.guix.info website, the Guix-HPC website, you can find a list of channels so it's only scientific channels and only some of them, but at least that's a start. So you can perhaps find what you need there.
Thanks a lot.
Ludovic, I didn't really get the difference between Guix-HPC and Guix.
Oh, so Guix is a software. Guix-HPC is just an effort, just a collaborative effort specifically to try to improve Guix for the HPC use cases and for reproducible research. Guix-HPC is not software, right? It's just a shell, so to speak.
Okay, and so there are other shells for other communities than HPC?
No, not yet. I remember someone wanted to create something similar for functional programming, or was it something? Yeah, something like that. But that didn't happen yet.
Okay. And so I had another question about using auto tools, because sometimes, well, lots of the times, you can install, when you do configure, you can activate or deactivate some features with a configure -- with something.
Mm-hmm.
And so there are packages where there are many of those options. And so it makes it very difficult to have the exact same version as the the person who published the paper and who used that software. And so can we put inside the definition of the Guix the Guix text file where we say, for example, I need StarPU, but I would need StarPU with OpenMP and with CUDA feature. And can we set these options inside the needs?
So in Guix, you would in your package definition, you would say I depend on this StarPU. So you would refer to a specific StarPU variable. So for example, we have a Guix-HPC channel so that's a channel. That's also the name of a channel that contains package definitions for scientific software like StarPU, for example. And we have a bunch of variants of StarPU. So one with MPI, one without, one with SimGrid support, one without, things like that. And so you can say specifically which variant you depend on. And so that's more than a version string, right? Because it also says that you've enabled that optional feature, that optional dependency, etc., etc.
Okay, thank you.
All right, so maybe it's time to wrap up, right? I suppose. So yeah, this is a big picture I showed at the beginning. So we have on one end software heritage, on the other end rescience, and hopefully Guix can help bridge the gap from source code to reproducible software deployment to reach that grail of reproducible research. I talked a lot about packages, a little bit about environments. Guix can also take care of environments like virtualenv, also container provisioning, like we saw with Spack, for example, but it can also take care of entire systems, which I did not mention so far, but that's an interesting thing if you're into it. As a conclusion from my experience at INRIA as a research engineer, I've seen people like over the last decade, initially, there were people that would not use version control, for example, like people working in numerical simulation. And over time, with training sessions and so on and so forth, people starting to use version control, and now most of them are doing it, and they don't look back, right? I think we also need to go in the same direction when it comes to deployment. Lots of people nowadays are still doing non-reproducible deployment, where they use modules or they install things by hand, or using non-reproducible methods. And we need to add reproducible deployment to our good practices book. And this is it. I'm sorry for being somewhat late.
Good morning from Bern, Switzerland. So over the next half hour or so, I'm going to talk a little bit about Conda and CondaForge. First, from the perspective of a user, or more specifically, maybe a researcher. Then from the perspective of a maintainer. And finally, I'm going to take a step back and look a little bit at how these tools fit together into the larger picture. Full disclosure at the beginning, so I'm neither a developer of Conda nor an administrator of CondaForge. And until Evgeny invited me to talk a bit about this topic, I signed up to this hackathon just as a participant. So since I'm not a member of TREX, let me maybe very briefly explain my interest and my background. So I originally studied physics, and then I came into computational materials science via experimental physics. I've been a user of density functional theory and many-body perturbation theory codes. And I've done some development, some method development, but I'm not currently in the developer team of any of the big codes. But during the last 4 years at EPFL, I've been involved in the development of the AIDA workflow manager and the Materials Cloud open science platform. In these projects, we are in contact with developers from another European Center of Excellence called MAX. And this center collects a number of groups working on density functional theory and many-body perturbation theory codes. And so in this effort, I've helped some of these developers to get their codes on CondaForge in order to make these codes easier to install for novice users. And just as a last point, Monday next week will be my first work day at Microsoft Quantum, where I will help setting up a quantum chemistry service powered by Azure. And so my interest in participating in this TREX hackathon was not so much focused on a particular code, but more on exchanging experiences and thoughts and on build systems and on package management in general. And part of the goal of this talk is also then to stimulate a bit of discussion on these topics and to hear about your experiences and thoughts on this topic. So if you attended Evgeny's sessions on AutoTools, you already used Conda. And so this is what the Conda's documentation says about Conda. Conda is an open source package management system and environment management system that runs on Windows, macOS, and Linux. Conda quickly installs, runs, and updates packages and their dependencies. Conda easily creates, saves, loads, and switches between environments on your local computer. It was created for Python programs, but it can package and distribute software for any language. So to me, these are, I underline here the parts that are the important ones for me. It is a cross-platform package manager, and contrary to tools like apt or yum, it's not installing things on the operating system level, but you can create individual environments similar to what Guix does. They claim it is quick. We will see later whether that is actually true all the time. And finally, so while Conda was created for distributing Python software, it really can be used to distribute software in any language. And that is a common misconception when people first start interacting with Conda. So now how do you specify such an environment? Here I'm just taking Evgeny's example. So you have this environment.yaml file, and what you need to tell to create the environment, you give it a name. You tell Conda which channels to pull from. So these are kind of the online sources of precompiled binaries or source codes. You tell it what are the dependencies that you need. And in this particular case, Evgeny also specified a set of environment variables that will be set when the user enters the environment. And then all you have to do as a user is to run these two commands. So first to create the environment, and then to activate the environment. And so what this means is that as a researcher, when you publish a new paper and you would like to enable your readers to rerun your calculations, for example, in the case of material science, maybe run these calculations for a new material that you have not included in your study. All you need to do is to provide this environment.yaml text file, and it becomes very easy for readers to set up the computational environment on their computer. And so I just wanted to quickly show you an example to get an impression of what this means from the perspective of the reader of a paper. So this paper here is not from our group. This is from the group of Jörg Neugebauer at the Max Planck Institute for Iron Research in Düsseldorf. So let's have a quick look at what you get here. So if you click on that link, we get to the to a Git repository that in this binder folder contains this environment.yaml file, which in here specifies again 2 channels, and it specifies a number of dependencies. Let me check something here. So and now what we would do as a researcher, we would go to this repository and we would clone the code. So we just do git clone repository. I've already done that. Then let's go to this binder folder and have a look at this environment file. Yeah, so for example, it installs a specific version of Python, a specific version of this LAMS force field atomistic simulation code. It installs there a specific version of their Pyron workflow manager and a couple of other things that you need. And now what we need to do is we need to create the environment, as I explained before. We just do conda env create -f the file name, and then we also can give it a name. So let's say TREX demo. And so what Conda will now start doing is it connects to the channels that we have specified here, downloads kind of which packages are currently available there, and then it tries to resolve the dependencies that we have specified here. As you can see, it's taking quite a bit of time. And so I will quickly switch. So one trick you can try is that there's a different, the kind of a drop-in replacement of Conda that's called Mamba, that is designed to be a bit faster in this package resolution. You can install it via Conda, and then you can just use Mamba instead of Conda. While this runs, I see there's a question by Lionel. Just ask. And by the way, next time if someone has a question, feel free to just shout into the chat, because I might just shout, because I might not always see when there's a hand up.
Yes, why are there two channels here?
Sorry?
Why are there two channels in this environment?
This is because not all of the software that they need are available from one channel. That's what I guess. I don't know, to be honest, which of these softwares are only available in BioConda, or well, maybe it's just even not necessary, and all of them are available from the CondaForge channel. Yeah. Does it answer the question?
Yes, thank you.
Great. So now it's it has resolved all the dependencies, and now executing the transaction means it's actually creating this environment for us. This should take a few more seconds, and once that is done, we can just enter the environment. While this is still running, let's maybe have another look at the Git repository. So what they provide here is a kind of a scripts folder with a couple of Jupyter notebooks. And so the idea is that this environment.yaml specification already includes all of the tools that are necessary for a reader of the paper to then run this Jupyter notebook. So now the environment has been created, so I just activate it. And so, for example, if you're from that field, you will know that the executable of LAMPS, it's called called LMP underscore and then underscore MPI for an MPI version of the executable, and LMP underscore serial for the serial version. So this executable has been installed. And we can also have a quick look at one of the notebooks that they have here. So Jupyter notebook script.ipynb. This now opens a Jupyter notebook server in this environment that I've created. And the idea is that now I'll be able to kind of work through that Jupyter notebook because all of the dependencies have already been installed. I'm not going to do that, not to waste time. Maybe one last point. The Zoom gets in the way. So there's also this my launch on Binder button here. And what happens when I click here? So mybinder.org is an organization that runs mainly on the donations, and they are running several large Kubernetes clusters. And when I click on this button, what happens is first kind of a Docker image is built that contains all of the dependencies that are specified in this Binder folder. And then a new port is created on that Kubernetes cluster that runs this image. And I'm now connected to this port that I have just here for my own. And so I can, sorry, we don't need to go to the Binder folder, but maybe to the scripts folder. And so I can open the Jupyter notebook here. And so essentially what this has done is it has saved me all of the steps that we've just done. So to create locally, first of all, I don't need to have any software locally installed. This is all running in my browser, and I don't have to create the environment from the specification, and I don't have to enter it. This has already happened when I enter here into that environment. And so obviously, so this has been essentially been replaced by a single click, and obviously that is can be very useful for novice users who maybe not familiar very well with the command line. Let's go back to the presentation. Yep. So so far we've talked about Conda. Conda is the package manager, and Conda Forge is a so-called Conda channel. So it's a repository of pre-built software, and different from the Conda default, the default Conda channel, which is maintained by the Anaconda company. Conda Forge is a community project, and some nice things about Conda Forge. So it has a very nice pre-configured continuous integration setup for building new packages. So you don't have to build new packages on your computer. You can just create the specification, and it will build it on I think on Azure, on runners in a pre-configured environment. For maintainers, it's quite easy to keep packages updated. So for example, if the source code of your software is on GitHub, a bot will monitor that repository for new releases and create a pull request to your build recipe whenever a new release is made that already points to the new tarball of your code, so that in many cases you can just look at this pull request and approve it. But of course, sometimes, for example, some dependencies change and it's not fully automated. So you still need to check. And then finally, because of this, many material science code are already there. So this is a list I compiled for the Max Center some time ago for kind of the simulation codes and the libraries that are built by that center. And you can see many of them are already on Conda Forge, and we have been working on, for example, adding more like the Fleur code. Here's some more statistics. So I mentioned that Conda is multi-platform. Of course, it's one thing for the package manager to be multi-platform. What matters is how many packages are actually built for the different platforms. And so here on the right, you can see that Conda Forge is not only targeting different operating systems, but also different processor architectures. So for example, Linux on ARM or macOS on ARM. No Arch here means packages for interpreted languages like Python that should be mostly architecture independent. If not, you have to build one. You have to make them one of these packages. If not, the maintainer of the package will make them platform dependent. So the number of packages built for macOS, for example, is almost as large as the number of packages for Linux. Windows is a bit less, but also quite substantial. And then now the builds for the new ARM architectures, they are still smaller, but they're growing. And so partly this is because maybe because the Python community is so large, and there's been this drive to use Python for data science. There is quite a large number of maintainers, so there are about 3.4 thousand people maintaining different packages on Conda Forge, and there are 29 members currently on the staged recipes team, who are kind of the entry point into kind of monitoring the entry point into Conda Forge. So it's their review that you have to pass when you want to add a new package to Conda Forge. All of these are reviewed. And so what do you need to do to get your package on Conda Forge? It's actually quite straightforward. So to submit a package to the Conda Forge channel, add its recipe and license to the staged recipes repository and create a pull request. Once the pull request is merged, the package becomes available on the Conda Forge channel. Note that contributing a package makes you the maintainer of that package. And so let's also have a very quick look at how that looks like. So this is the staged recipes repository. And so what you would do is you would simply fork that repository. And then what you need to do is you need to modify one file, which is this template meta.yaml file. So let's maybe briefly go through it. You will know some of these things now already from Guix. So first of all, you tell the name of the package, the version it has, where to get it from, what the hash of that source archive is, so that you can be sure that you're actually getting this, what you're expecting. Then you explain how to build it. So for example, if it's a Python package, you can simply leave that unchanged. If you're building a source code, you will simply delete that line and it will run a shell script, for example, build.sh, which will then call make or cmake or whatever build system you have. You specify the environments during build time and during runtime for your package. On CondaForge, you are expected to add tests to each of your packages that to make sure that what you're getting is actually working and not broken. And then there's a couple of metadata, like the license of the file of the package, a quick description of what it is about, where to get more information, and then importantly also who are the maintainers of that package. And so let's have a quick look maybe at one of the PRs. Yeah, maybe just to see how I get there. So I mentioned this Fleur code before. So I have an open PR to add this Fleur code. It's I currently still have some issues with there are some issues at the moment with the build system of Fleur, which is why I've currently not requested a review from the package from the CondaForge maintainers, but we can still have a quick look at what this PR contains. So the first file that I'm adding here is a license, the license of that code. Then here is the shell script that I mentioned that will be executed on this cloud machine that is building Fleur when it's being added to CondaForge. So here, this is useful in most of these scripts, so to say that abort on any error and print all of the commands that you're executing, setting some environment variables. Many of these actually, so many of the flags are already managed by CondaForge, and you don't have to specifically set them. And then I'm just configuring and making. And here below is now our modified meta.yaml file. Again, name and version of the package. Here, I'm saying skip the build if you're not on Linux. So usually it's a good idea to start with the Linux build. It's the most widely supported. And what I then do is once the Linux build works, I start adding more operating systems as supported, of course, by the code. Then this code will needs both a C, C++, and a Fortran compiler, as well as a number of libraries. One thing to note here is that the default for C and C++ on CondaForge is Clang, while the default for Fortran is Gfortran. I have had cases where this leads to problems, but you can explicitly request a specific. First of all, you can request GCC if you want, and you can also request a specific version of GCC. All right.
And a specific version of other things too?
Yes, of all of the other things as well. So let me bring back to the presentation maybe. Okay, so here's some personal thoughts on Conda and CondaForge from me. I really like this YAML format. I think it's very intuitive, particularly for the environment specification. So what the user has to do in order to specify the environment. It's still true to some degree to this meta.yaml file that we just saw when you specify your package. It's true a bit to a lesser degree if you start having multiple variants of your package with MPI, with OpenMPI, with MPCH, with serial version, and then maybe more. But I think it's still a good format. Of course, the packages are pre-compiled, so for the user, the installation is fast. Typically, the packages are more up to date than the ones that you would get from, for example, apt. The community is quite large, and I found them quite friendly. And yeah, this is just a little bit of cleverness. So the way Conda, the packages are compiled, it's setting the R path to the binaries and libraries and so on of the environment, so that even if you want to combine executables from multiple environments, you can typically make it work with too much hassle. But there are also some downsides, of course. So so for Conda, Conda Forge, there's no build from source. All of the Conda Forge packages are built on CI, and if there's no package there for your operating system, you're out of luck. What you should be doing is you should be adding this operating system to this build recipe. And then there's less reproducibility guarantees than Nix. So for example, you saw this shell script that is building this Fleur code. In principle, I can download stuff from the internet there. And of course, the internet will not be the same today as it is in 3 months. And so so this can make builds less reproducible. One aspect is important for HPC is that there's more of a focus on portability than on performance, at least at the moment on Conda Forge. So one of the default compiler flags, for example, on the Conda Forge runners, will use the no-Conda microarchitecture, which is a very old one that, for example, does not have AVX instructions. Of course, the idea is just that these packages should be able to run on many different, on as many kind of processors as possible. So there are some packages, you can definitely change that when you build your package. So you decide what microarchitecture you are compiling for, and some packages provide versions for different microarchitectures, but it's something to keep in mind. And then the last point that I mentioned, so dependency resolution can be slow and maybe even worse. So if you have a kind of a set of dependencies that when the dependency resolution fails, the error message is usually not very helpful. By the way, Lionel, you're still unmuted. I'm not sure whether you know it. Okay, and so that's all what I wanted to say about the practical aspects. Sorry, Johan. Go ahead.
Yeah, thanks. So where are the binaries produced? Is that on the Conda or Conda Forge server?
Yes.
Okay.
So all of these builds are happening publicly, and you everybody can go there and look at the logs and so on. Okay.
And then if one would propose to have it built for some particular architecture or so, then one can make it in the form of a pull request? Or...
Exactly. So all of these are then so let me maybe quickly just to give an example of this, because this is something I forgot. These are called feedstocks. And so all of these are in the Conda Forge team. And then you have, for example, this is the feedstock for Quantum Espresso, some like a density functional theory code. This feedstock is automatically created once the pull request to the stage recipes repository has been reviewed and merged. And here you then have the build recipe for Quantum Espresso, for example. And if you now wanted to add a new architecture here, you would make a pull request to this feedstock, and the maintainers of that feedstock will then have a look and hopefully merge it.
Okay, thank you. Thank you.
Otto, you also had a, so Manu is first. Sorry.
Yes. Can you explain the difference between Mamba and Conda? You used the Mamba a few minutes ago.
Yes, I'm not even an expert on the differences and what the differences in the implementation are. You can just think of Mamba like a drop-in replacement for Conda that does maybe more clever caching, more tricks in the dependency resolution. I don't even know the details. So it can just speed up your life, but you can also just use Conda.
Okay, thank you.
Cheers. Otto?
Yes, I would like to just point out that if it depends on the build on the CI system, it basically, for example, now we are computing a lot of things on Fugaku supercomputer, which is a very special architecture, like microarchitecture, and it requires their own libraries and proprietary compiler. So, and I think it's not possible just to put this compiler inside the CI system. So
that's true.
So in this case, cannot be used.
I agree. So that is one of the downsides of Conda Forge is that it's so I mean kind of you have to make it available for everything and for everyone online if you want to have some very special version of it, and it's not so easy. So it's not easy to say I want this version of the package, but I'm now going to locally build a version for my very specific version of this library dependency or for that proprietary compiler or something like that. So this is something where I think Guix is Nix and maybe even more Guix are better suited. Conda, of course, has an advantage of being a very large community and of having a really large number of packages and libraries already there.
Well, I think even Guix Nix cannot do something about it, because if I believe Guix cannot use this, it uses GCC, right?
Mm-hmm.
And I don't know if GCC can compile on Fugaku microarchitecture. And even if so, I believe it will use just a subset of the microarchitecture.
I would suggest to ask this in the chat to Ludovic how you can switch compilers in Guix. I would also be interested in that. Thanks for the question. So let's maybe continue. Let me again move away from Zoom. So that's all I wanted to say about the kind of the practical aspects of Conda and Conda Forge. Now maybe for something more abstract. So we've been talking in this hackathon about package managers and build systems. I think we intuitively have an understanding of what the differences between those is, but there's also quite some regions of overlap. And so it can be helpful to maybe take a step back and think about what we mean by these terms. So this is an abstract definition of a build system from this article, Build Systems à la carte, which is an article I can recommend to anyone interested in kind of a high-level view on build systems and what differentiates them. So build system takes a task description, a target key, and a key value store, and returns a new store in which the target key and all its dependencies have up-to-date values. So let's have a look at a couple of instantiations of that definition. So one, of course, is a make. So in make, the key value store would simply be the file system. The keys are the file names or the file paths, and the values are the file contents. And the task descriptions are the makefile rules. So that's, I think, what we all think of when we think of build system. Now for another build system, Microsoft Excel. Maybe not what comes to mind when you think when you hear the term build system, but when you think about it, it's actually quite closely related. So in Excel, the store is the worksheet. The keys are simply the indices of the cells, and the values are the displayed cell content, so numbers and strings. And as all of you know, in Excel, you can enter formula into cells that then make the displayed value depend on the value of other fields. And so then figuring out what the displayed value should be is then the task that the build system has to solve. So that is the analogon to the makefile rules in make. And finally, let me also put Conda on this list. So for Conda, the store is the environment. The keys are the package names, and the values are the package contents. And then the task description would be this specification of the environment, maybe that environment.yaml file, which includes also which versions of packages, which variants of packages I want, etc. And so, yeah, read from this angle, the difference between a package manager and a build system is mainly about granularity. So a package manager operates at the level of packages, while what we typically mean by a build system operates on the level of individual files. This slide is just to mention that the kind of dimensions along which the build systems differentiate themselves when you look at them at this abstract level. So are, for example, you can differentiate them by the information that is stored between successive builds. Make, for example, relies just on file modification times. Then you can differentiate them by whether they support the creation of dynamic dependencies, how they are scheduling the tasks, the dependent tasks that you give to the system, whether they are minimal, meaning that it is guaranteed that in a given execution, no task is run twice, whether they realize when an intermediate output is unchanged and therefore all of the dependent outputs are also unchanged and therefore don't need to be rebuilt. And then finally, whether they are integrated with some cache in the cloud. But so these are maybe not the kind of criteria you typically think about when deciding which build system to use or which package manager to add your code to. And so here I've collected a couple of practical criteria one might think about when considering which package manager to pick. Of course, there are many more. So one is the operating systems that are supported. Then whether they are publicly maintained binary catalogs and also what the reproducibility guarantees are. And finally, it also matters how large the community is, how much work has already been done, and therefore doesn't need to be redone by you as a maintainer of the build recipe. So in the last column, I'm looking at a set of 24 open source simulation engines. These are the 24 atomistic simulation engines that are cited more than 100 times per year, according to Google Scholar. And you can find all of them on atomistic.software. And so we can see that EasyBuild and Spack and also Conda Forge, I think they cover more than 70% of these simulation engines already. Nix has a bit less, and Guix has again less. Of course, it is not to say that this situation cannot be changed, but this can be a bit of an indication of how much work would be needed on the maintainer side, for example, because oftentimes it's not just adding the package for your code, but you might also need to add packages for the dependencies of your code, etc. And so, yeah, so I hope that these slides stimulated your thoughts and maybe also some questions. I have a couple of points myself that I think would be great to discuss. So the first would be just to share the experience that you have had with package managers in the HPC space, Spack, EasyBuild, maybe some of you have already used Nix or Guix or others. Then whether you've come across any particular trends that you see on the horizon, whether maybe you have any particular specific hard requirements that a package manager needs to fulfill in order to be useful for your application. So for example, being able to work with a specific commercial compiler would be one. And then finally, I mean, it would be really great if we could identify maybe a couple of promising solutions that we think are doing things right, and maybe doing things right good enough now, and maybe some interesting for the future, so that we can kind of focus our efforts when we decide where to invest into adding our codes to the package managers to make it easy installed for users. And of course, if you have any questions, feel free to reach out to me via email anytime. Any thoughts, any comments, any questions?
Leopold, I have a question. Can you hear me?
Yes.
Yes. So in the previous slide, you showed some the differences, yes, between EasyBuild, Spack, Conda Forge, etc. So I would like to know why Conda Forge you put reproducibility guarantees medium, and why on Spack and EasyBuild it's weak. What makes Conda Forge more reproducible than Spack or EasyBuild?
Yes, so the difference between Conda, so of course, first of all, I should say that this is my personal judgment, so this is not necessarily the objective truth. But what I meant here is that on Conda Forge, all of the packages are built on these runners on continuous integration. And so if you know which runner was working at a particular time, then at least for the execution environment, taking away the rest of the internet, which these build scripts might interact with, is well specified. While with Spack and EasyBuild, I mean, it really depends on what libraries you currently have installed on your computer, what compilers you're using, and some person might use something completely different and not remember in 3 months what exactly they did.
Yes, but so I don't know about EasyBuild, but with Spack, I know that you can really specify the version of each package that you need in your requirements. So you can say, I want to install this package with this version of MPI with this particular feature on. So it seemed to me that if your Spack package is well specified, that you can really have something that's reproducible. And so with Conda, I had this impression that the fact that you couldn't really have a fine granularity on the compiling options and on the versions. So I had the other impression. So that was the point of my question. But
I agree that there's less freedom than in Conda Forge than with Spack. I would say that's rather makes it easier to reproduce things than harder. But as for the specifying the versions of dependencies, I mean, in my experience, it's basically not possible to specify the versions, the dependencies of a package to such a degree that you can be sure that it will never break, because your dependencies have again dependencies, and they might depend on those dependencies in a rather weak or let's say easy to break way. And so I mean, I think the difference with Spack and EasyBuild is really that they depend on part of your operating system, while at least with Conda Forge, all of them are built on the same system on CI. But to me, this is, I mean, how big this difference is in practice, I mean, I don't know.
Yes. Okay. And also with Conda, you're sure that everybody has the same setup. So I mean, you don't have one personal build for each person. It's more homogeneous.
Exactly. That's exactly what I mean. And so all of the people running a specific version of a package on the same operating system will have the same binary code.
Okay, thank you.
Next is Otto, I think. Or did you still have your hand up?
Yes. Hello. I would like to ask. I addressed this issue. I don't know if you remember at the IDA workshop. But to what extent is Conda open source? Basically, you have plenty of open source licenses, but it's not community driven. It's driven by Anaconda company, right?
So the Conda package manager is open source, but what the Anaconda company does is they maintain this default Conda channel. And so there, if you want to have like certain features, like, I don't know, I don't even know exactly what you can pay for, but you can pay for things like support, I think, and having like super well optimized packages or something like that. But so
yes. My question is, can I fork the Conda thing and have my own branch? Because some open source license can forbid this thing, because this was one thing that concerned me with Conda for a long time, is basically maintained by a company, and they introduced a lot of new features compared to, for example, I don't know, virtual environments. And I was always afraid if the company something do this, I would be, and a lot of my software will be rely on Conda. I will be stuck because I have to pay for something. But Yeah, it's BSD3. Okay, so it should be possible to just fork the older version and use the older version. Okay, thank you. This was really was concerning me for a long time. Thank you.
Okay, cheers. Next is Evgeny.
Yeah, hi. Thank you for the presentation. I was wondering, it's a bit the same question as Anthony had before for Guix. Basically concerning the JLibC library. So, so when you say that, so I understand that it's built on the cloud in the cloud instances. So Conda does not depend on any system-wide library, or
this I cannot say, and I think you're right that I don't think it will install the glibc, but I should check, and I don't know it. I should check it
because this can be an issue.
Yes.
Yeah.
No, so Conda does not give you perfect reproducibility in that sense.
I know. It depends on the glibc being on the local computer. I know because it doesn't work for an old computer.
Okay. Thank you.
So maybe does anyone else want to share maybe some thoughts on past experience with package managers? I don't know, with also with the community, maybe in Spack or EasyBuilds, or any of the new ones. I'm particularly interested if somebody has used maybe Nix or Guix already. And I mean, if something comes to your mind, I mean, please feel free to just drop me an email. And yeah, so I'll be probably thinking about this this topic for a couple more months. So I'm very happy to interact on these questions.
Thanks a lot, Leopold, for this presentation. And so you will be around today for the hands-on session?
I will see. So there's a couple of other things I have to do. I mean, if there's something I could contribute.
No, because I was thinking maybe some people will try to make a package for Conda Forge today, and
okay,
I have some questions to ask you.
If that is the case, please just let me know in the channel, and then I will make sure to help you guys if you have any questions.
Okay, so then I will create a channel for that if needed, so that it will concentrate the information.
Sounds good.
Okay, so thanks everybody, and then we can move on to the hands-on session again, so that you can continue working on your CMake auto tools, or even try packaging for Guix or Conda. So so then I will ask Julie or Jacopo to open the breakout rooms, so that
Anthony, yes, I will open it now.
Awesome.
Thank you.
I'm gonna share. Okay, can you see my screen?
Yes, we can see lots of little slides.
Can you see a big slide now?
Yes.
Okay, great. All right, cool. So I didn't know exactly how to target this because I figure that people have just done a lot of hands-on stuff with CMake and Auto Tools. So this is going to just be an overview of Spack and sort of where it fits into with the other package managers that you've already heard about. If you think about what Spack is for, and you've probably heard this from other folks, it's for building gigantic dependency graphs. So if you look at modern simulation codes or scientific software in general, they rely on tons of libraries. And so, I mean, you've probably seen this from Guix and from Conda and so on, but the MFM is sort of a small domain-specific library with all of its dependencies. And in a fairly typical configuration, it's like 31 packages. LBAN is a neural net library. It's similar to things like TensorFlow. It just uses MPI. That's like 70 packages. And then our larger sort of workflows that we run can exceed like 100 packages. And so if you're a developer working on a project like that, and you're putting all these components together, you probably don't want to run configure, make, install, and fight with it for all 100 packages. You probably want to have something automate that process. And Spack is a package manager. It's designed to do that. And if you think about what your typical package manager does, and I guess you've heard about some atypical package managers already, I'd say Conda looks a lot like RPM. It just runs in your home directory. Things like these often assume sort of a one-to-one relationship between source code and binaries. And so, if you have some source, Debian has this reproducible builds project. And so you can go and build the source, you can install it, and they checksum it and they say, okay, that's the binary that corresponds to the source. They build portable binaries so that they run on lots of machines, and they sort of assume that there's like one tool chain for the whole ecosystem, so that that there's a standard Conda stack that you have to contribute to. They've pinned certain compilers and certain versions, a certain libc and so on, that you have to build with to make binary packages for that. And for Guix, I think you can customize things in Guix as well, but I think the typical builds in Guix are sort of targeted at particular compilers in the repo. And maybe Ludovic went into more details on that earlier, I'm not sure. Either way, there tends to be a sort of fixed tool chain. Spack is not like this. It's designed for HPC, where we sort of assume that the code is going to get distributed from source, and that there can be tons of variants of the same package. You may want to build the same code with different MPI implementations. You may want to build it with different math libraries. You may want to do different flags or different combinations of dependencies and so on, different versions. All of those things are what we're trying to enable. And the rationale there is really that you want to optimize for the machine that you're on. We want to build for a really diverse set of machines, because it can make 10 to 100x performance difference to optimize for the machine. And we also rely on system packages, in that you can configure Spack to go point at your system MPI. So you can say, okay, I want to use this MPI and I want to build all of these packages on top of it, using that MPI. The other assumption that we make is that and Conda and Guix don't have this problem, but it's a multi-language ecosystem. HPC codes are built from C, C++, Fortran, Python, lots of different things. We can't have sort of a language assumption. It's not like pip, where it's just where it's mostly just for Python, although they're finding that they can't get by with just that, and people are putting more and more things into pip. There are many different languages that we have to use, so we're not a language-specific package manager. And so if you look at Spack, it's designed so that you can clone it from the repo and just get going. So you say git clone this URL, github.com/spack/spack, and you can say Spack install HDF5, and it'll build that library with all of its dependencies. And HDF5 itself is actually pretty complicated. If you look at the dependency graph of HDF5, it depends on things like zlib, it can depend on MPI, other compression libraries, and so on. And you may want to build it lots of different ways. Different codes are written to different HDF5 API versions, and so you may care about the specific version of HDF5 you want to install. And so Spack has a syntax for that that looks kind of like this. I'll get into this in more detail later. And so we're really trying to make things as easy as sort of the mainstream tools like NPM or pip or things like that, but with customizations for HPC so that we can actually install custom versions of things. Spack, in addition to having this sort of CLI for installing packages, it generates modules. And so for each of those packages, we'll generate an environment module so that you can say module load package or module unload package. Spack has its own sort of thing that doesn't require modules, where you can say Spack load or Spack unload, and also supports environments, sort of like Conda. It has this virtual environment concept built into it. And it has a whole lot of DevOps features. And I guess I would say if you're comparing Spack to Conda, the fundamental difference with Spack is really that it was built as a from source package manager from the start. And the builds and the binaries that Spack does are really an optimization on top of that. So in that sense, the model for binaries in Spack is more like Guix. You start with a from source build and you can cache it. And if you end up with a build that you're trying to do again, you can install it from binary. Whereas Conda, you basically package everything up as binaries, and the user only ever sees the binaries. And I'd say the difference between both of those tools with Spack is really that we have a lot of developer features that enable you to sort of mix sources and binaries. And so we don't really see that much of a difference between, say, installing half your stack from binary and building parts of it, or just installing the whole thing from source or installing the whole thing from binary. We're sort of in the middle and trying to encompass both of those use cases. Spack's used on a lot of fast machines. It's used for to build the stack on Fugaku and for Summit and Sierra. And it's part of the US Exascale project. And so I don't know if people are familiar with this, but the Exascale project in the US is, it's actually a big software project. And it works with the facilities so that are deploying exascale machines. But the goal of ECP is really to build an exascale software stack. And inside of ECP, there are something like 80 or 90 different software projects and like 25 different applications that use them. And the challenge with ECP was really to take HPC development onto GPUs, because the exascale machines, they're all GPU machines, and to provide some portability across GPUs. And in doing so, to make the stack more modular, to basically be able to leverage a whole bunch of different libraries so that application developers don't have to rewrite everything from scratch. They're using frameworks like Raja and Kokos. They're using math libraries. They're linking all that together in a big application like the one you saw before. And so within ECP, Spack is the most dependent upon project. It's not the most critically dependent upon project, because you could build this thing yourself. If Spack went away, you could still build your code. But they are using it to integrate all these different packages. And so all the different pieces from ECP are sort of shipped in this distribution called E4S. The community for Spack is growing. We started in like 2013. And that was where I was just trying to automate what my grad student was doing, because I had a grad student who she had like 10 different libraries in her stack, and she was having to manually configure, make, install all of them and get them to go together. And so for a while, it was basically just a Livermore project, but we've started to get contributions from all of these other organizations here. So now there's like over 5,900 packages in Spack, and I think we have over 900 contributors for all time, which is pretty cool. And on the documentation site, these are basically places where we've seen people access the docs site. And we have close to 5,000 users monthly now, which is pretty cool. I don't think I ever thought this would take off the way that it has. It's pretty busy to maintain a project like this, because essentially, if you think about the configure and CMake stuff that you've been learning, Spack has this library of these 6,000 packages. And they sort of wrap the CMake or AutoTools invocations for all the packages. There's more than just those two build systems, but essentially, if you think about it, Spack is a bunch of templated build recipes for packages. And so there's constantly updates coming in from people who figured out how to build a package in a new place, or who figured out that a new version exists, or so on. And so, in a month, we might merge like 500 pull requests to the project with all these different updates. So it's definitely a community project, and it's not just one person doing this, it's people from a lot of different sites. And so if you think about sort of the core of Spack, like I said before, the UI at the most basic level just looks like it's an install command. You would say Spack install a package, and then it would say, okay, I'll get you a version of that package. And I'm assuming you don't care about any of the details. You just want me to get you a working version of that. So it goes and installs that thing and all of its dependencies. You can say Spack install MPI leaks at version 3.3, and that's a custom version. You can say install it with this compiler. So % means build it with this compiler at this version here. You can have options on the packages, and so you can say install something with a build option. And if you're coming from CMake or AutoTools, this is like a -D enable threads or a -- with threads or something like that. That's what it would translate to underneath. But we sort of provide a higher level API on top of that for users to configure packages. You can inject flags in the build, and so we record provenance on things like the C flags or the C++ flags, where you're actually specifying, what flags do you want the thing to build with. You can target specific microarchitectures. So one thing Spack knows about is what compiler flags correspond to different instruction sets for different generations of chips. And so you can build for like Skylake, or you could build for Cascade Lake, or x86 v4. Like the new optimized generic x86 levels. we have those targets built in. And the cool thing about this is, you can swap in lots of different compilers and they have different flags for these things. So you don't have to remember that. You just have to remember that you're building for Zen, right? And you would say, okay, I want to build for this AMD Zen architecture. The syntax goes on, but basically you can compose all these things and build different variations of a package. And it applies to the dependencies too. So you can say, I want MPI leaks built with this MPI implementation. And so you could say caret mpitch and say, I want to build it with mpitch, or you could say mbapitch, or you could say openMPI. It makes it very easy to sort of combine and explore the sort of combinatorial build space of packages. To enable that, we have a DSL for Spack packages that's it's pretty powerful. Every Spack package is just one package.py file. And so if you compare to other systems like Conda, I think the recipes are sort of per version, or I guess they're maintained over time in like a feedstock, and they maintain different versions. But Spack is designed to basically generate all of these different binaries from this one template. And if you look at how it works, this is for CryptKey. It's just a mini app that we run at Livermore. Every Spack package is a class. It extends some base package. You don't have to extend a particular build system, but you can. And so this one is extending CMake package because it's using CMake to build. And this takes care of all the common cruft that you have to do with the CMake package. It takes care of things like the build type, like whether you're going to do release or debug or rel with debug info, things like that. It has some common variants, and it handles things like rpathing and CMake that can be complicated. The top part of this package, there's really two parts to every package, is metadata. And so this is the homepage. This is where you can find information about it. This is the URL. The thing that's different with Spack is that all the versions are in this package. So it's telling you can download 1.2.3, 1.2.2, and so on. And these are the checksums for downloading the tarballs for those things. And then all the different ways that you can build these things are also in the package. So this says I can build with MPI, I can build with OpenMP, and these would translate to like plus or minus OpenMP on the command line. And so you can imagine that using this, you could build a lot of different combinations, right? You could build 1.2.3 with OpenMPI, but without OpenMP. You could build 1.2.2 without OpenMPI and with OpenMP, and so on. Dependencies are down here. This says I depend on some MPI implementation, so that's a virtual dependency. I won't get into the details of that, but basically you don't write your package to depend on OpenMPI in Spack. You say I depend on MPI, and you can swap in different MPI implementations. And this is contingent on the variant. So basically what this says is I depend on MPI when it's enabled. This is a dependency on CMake with a version constraint. So you're saying I need CMake at 3.0 or higher, and it's a build dependency. And so all of this stuff is really just defining the space of things that you can build with Spack. And the parts down at the bottom are telling you, these are instructions. So essentially, Spack itself is going to pick one configuration out of this space to build. And then it's going to pass that configuration here to the install method as a spec. And so that we call the configuration a spec or a specification. And essentially, all this does is it translates this spec into install instructions. And so it's a CMake package. And so here we're getting the CMake args. There's a separate build method that's basically inherited from the superclass. But what this is doing is it's saying, okay, I need to pass -d enable OpenMP to the CMake build based on whether this variant up here is enabled, right? So you just say whether plus OpenMP is in spec and whether plus MPI is in spec. This will be true if it's on and false if it's off, true if it's on, false if it's off. And basically that just translates the spec to CMake arguments. And so really, like for any package in Spack, you're writing a wrapper around the types of configure systems that you've learned in this course. And Spack drives that thing to build sort of different versions of things. And its job is to make sure that they're all consistent. It basically ensures that those 100 packages in that build are all configured and built in a consistent way. And this language allows you to specify how those packages should interact and what constraints should be on them. You can do more complicated things in Spack. So we've recently added, we have things like conflicts, and we have, architecture specific stuff in these packages. So with it's actually kind of interesting. Inherit from CUDA package mixin. And we have variants for this where basically you can enable or disable CUDA because we assume that most things are going to want to build, that most things can run either on the CPU or the GPU. You can have a conditional variant. So if CUDA is enabled, then there's also a CUDA arch parameter that you can set. And so that's what this when plus CUDA is. And you can have a conditional dependency on CUDA here. And so basically, if you inherit from CUDA package, you inherit all of these properties. And so your package will basically be set up to depend on CUDA and to have all of the different constraints that are associated with it. So like down here, CUDA package provides a bunch of different rules that essentially tell you when CUDA supports different architectures. So you can specify the architecture version. This is like the compute capability of CUDA. We know which versions of CUDA support which architectures, and we know which host compilers can build that work with different versions of CUDA. So this is basically saying, when I have CUDA enabled and I depend on CUDA up to version 10.2.89 on x86, I need GCC 9 or higher to run. And if I'm on PowerPC, the version is a little different, but this is the version at which it first supported GCC 9. And so what this does is it allows you to put constraints on things so that users don't get this wrong. Basically, if a user tries to run with a version of CUDA that doesn't support a particular version of GCC, then we'll fail and not make them go through all that pain of discovering that themselves. And this is, encapsulated in one package that you can mix into your own package. You don't have to do all this CUDA support yourself. You can say, I inherit from CUDA package. And we have another one for ROCm for AMD GPUs. So anyway, this is an example of sort of the more powerful things that we can do in Spack packages. And the other kind of cool thing is that it's one package.py that you inherit. And basically it can generate all these different builds because we put the rules in this sort of declarative way and we're able to figure out what the constraints should be for a particular scenario. All right. The process of converting from this up here, the command line syntax that Spack uses, to something that we can actually build is called concretization. And so essentially what happens with Spack is you would say MPI, you install this thing, MPI leaks with the call path library at version 1.0 with the debug option enabled, and libelf at this version. We'll take that and generate sort of an abstract graph where the details are not filled in. We don't know exactly what it is that we have to build. And then concretization goes and figures out how to set them in a consistent way. And so it fills in all the details, and then we store that on disk. We store all the provenance, and you can actually query it. You can say Spack find and query by all of these different attributes and say, of my 100 installs, which one has CUDA enabled, which one has different variants and things like that. The cool thing about this is that by the time you get to the build and by the time you're writing your build recipe, all of these decisions have been made for you or by the user on the command line or from some preferences. And so you don't have to do what a lot of build scripts do, which is basically poke at the system and say like, okay, is MPI installed here? Is it installed here? Is it installed here? And if it's installed here, is it this version? And basically query packages and try to figure all that out yourself. Spack will have set that up for you. And so the process of writing the build recipe is pretty simple. You just translate from this graph to something that you can tell CMake or AutoTools. There's no real decisions to be made other than just querying the graph. And once that's done, once we have a concrete spec, you can imagine that you have a graph like this. We hash that. And so this is a lot like Guix in terms of how things are installed. It's inspired by Nix, which is what inspired Guix as well. This graph, we basically hash the whole thing and we give every node in this graph a unique installation directory. So there's bzip, there's Python, and so on. And one thing that we do in Spack to keep you from going crazy with all of these different dependency versions is we set our paths on the libraries that we build. So in the Spack build environment, the compiler wrappers embed RPath flags so that the libraries that get generated know where their dependencies live. So like here, the Python in this directory would have RPaths in its libraries out to bzip2 where it needs it, or out to SQLite or whatever. And you can run a Spack executable directly from the installation directory without having to load a bunch of modules because of that, because we basically just, we put information into the binaries that tells them how to find their dependencies. Okay, so that's it for sort of the basic overview of what Spack does. The thing that we have built around this build model is Spack environments. And they're a little different from Conda environments because, I think we were sort of inspired by things like NPM and maybe Bundler for Ruby. We wanted a model where we could have sort of a manifest file that says what the requirements are for your build. And we wanted to be able to concretize that and save a lock file so that we could reproduce the build later. And so Spack uses this sort of manifest and lock file. In Spack, they're called spack.yaml and spack.lock. And basically what you do in an environment is you write this simple YAML file here, and you say, you might include some configuration or write some configuration in here yourself. But the core of it is this list of specs. And so you say, I want to install these specs. So I want HDF5 with libelf and OpenAPI, or I might want some other set of packages in there. This gives you a way to sort of treat a group of packages as though they're one. And so like you can activate an environment and you can say Spack install, and it installs everything in the environment for a user. And so you can put one of these in a Git repository, for example, and work on it and iterate with other people over sort of a common set of packages. And lock files will basically allow you to build exactly what somebody else built. And we're using this to build a lot of different features to support developers. So the fact that we have sort of configuration and declarative code requirements in one file enables us to build other sorts of workflows on top of that with configuration. So we have things like Spack external find, where you can get on a system, you can make an environment, and you can say Spack external find, and it'll go out and say, oh, there's CMake on your system. There's other tools that you might want to use, and it sets up the configuration for those things and directly in your environment. And so here, CMake, the package, actually knows how to detect itself on the system, and that'll generate some configuration in your environment to tell Spack where CMake is, and you can rely on that external CMake if you want. You can embed tests in Spack packages. And so like if once the thing is built, you want to run something like make check, or if you want to run, your own custom tests with the package, you can write those. And Spack knows how to test an installation after it was installed. The other thing that we've been using a lot, and I'll talk a little bit more about this, is CI, where you create a continuous pipeline in GitLab from one of these. And so essentially you write this YAML file, it gets concretized, it gets expanded into this large dependency graph, and we generate a bunch of parallel jobs in GitLab that build the whole thing. And you can rig that up with binary caching to allow you to sort of iterate on a stack over time, where basically you're tweaking a YAML file in a repo, or changing the recipes that it uses. And we actually use this for Spack's own CI, but you can use it for specific projects too. And then Spack Containerize lets you take an environment and turn it into a container image. And so we'll build sort of a multi-stage Docker recipe that gives you a container with all the stuff that you had in your Spack environment. So you don't have to write the recipe yourself. So I mentioned E4S before, which is ECP's sort of stack-based software distribution. And E4S is actually implemented as one of these environments. And so essentially, it's like 90 packages now. It's grown, and like 500 plus dependencies. E4S is just this list of all the different packages that are in ECP, and each of them is a Spack package itself. And there's a little bit of configuration to make sure that things work on different machines. And so, like for example, there's configuration for MPI down here. There's configuration for system CUDA, and so on for the different platforms that E4S supports. They have a binary cache of over 50,000, I think it's like 70,000 now, Spack packages. And they just released a new 2021.11 version of E4S with the latest versions of things. So you can think of this as sort of a little curated distribution that lives inside of Spack, and that ECP is maintaining over time. One of the things that we have added recently is something called Spack Develop, and Spack Develop is intended. Let me make sure I got this in the right order. Down here, or is it the TREX Hackathon? Spack Develop here. Okay, sure. Yeah. Okay. Yeah, we added this command called Spack develop to enable you to sort of actively work on a package in an environment. So if you have an environment that has, say, an application in it, and you want to work on 2 of its libraries because maybe you work on the libraries that support some application as opposed to just the application itself. You can activate your environment, you can add your application to it, and then you can say, I want to develop this library here at a particular version and this library here at a particular version. And then what that gets you is a directory structure that looks like this, where you have your Spack YAML, it looks like this down here, or there's my application, that's the thing you're building, and these are dependencies that you want to work on. They get checked out into their own subdirectories, and then you can work on them and rebuild the whole application together. With all of its dependencies in the configuration that you wanted, but with the source code that you've tweaked here. And so we're really trying to convert environments into a sort of developer workflow tool where code teams that maybe have hundreds of packages can work on different components together. We've had some success with this with the applied ML team at Livermore. They wanted to accelerate, they wanted to work together on different versions of PyTorch basically for a particular workflow. And every developer on the team needed to build PyTorch and Horavad and all of this stuff for PowerPC and the special MPI version that runs on Sierra at Livermore. And so what they ended up doing was they made a Spack environment that looks like this, where these are the specs up here. This is what they want to build. They have some package configuration like I showed before, and then they have some preferences about their Python versions, about their PyTorch version, the options that they build with on it, whether they want it with the distributed training or CUDA enabled, and some compiler preferences. And they're able to check this thing into a repo, and each team member is now able to basically clone that and build the whole thing in about 20 minutes with the binary caching that they're using. And we're trying to speed that up because I think we can get a lot faster with binaries. But before this, they spent a long time passing around build scripts and trying to debug differences between them, but this enabled them to actually create a reproducible environment that works on our machines. We are trying to support one of the multi-physics codes at Livermore. It's called Marble. And they actually sort of invented this, well, invented is sort of a stretch, but they had a workflow like this. And they work on a whole bunch of packages at once. And so they have sort of the packages, the core ones that they develop, which they call first-party packages. That's most of the hydrodynamics modules for this code. Second-party modules with the other ones that are developed by other Livermore developers, and then they have all these third-party libraries. And the difference is really that the first-party ones they're kind of always working on. The second-party ones they don't own, that they work on frequently and commit pull requests to other projects within a lab. And the third-party ones are typically installed just from a tarball, and they use the version that's out on GitHub. And so they don't. The workflow is similar to what you would see from a team using a monorepo like Bazel or something like that. But it's our teams are too distributed to do that, and the open source community doesn't really work that way either. In a monorepo, you kind of have to check in particular versions of code, and you have to keep checking in new versions as it evolves. And I think it's a bit less flexible than what we're trying here. What it gets you is that everything is sort of tied together, and you have a lot of control over the versions of things that you're building. And so what we're trying to enable is that same sort of workflow, but in a polyrepo scenario where we have lots of different repositories together. So the thing that we had to do to enable this was we actually added Git versioning to Spack. You can say, if you have a package that has sort of a Git attribute in it, you can now just say Spack install zlib at this hash, and it will go and check out that exact version of zlib. And internally, we actually go and look at the tag structure of the repository and try to figure out what version this hash corresponds to, so that the packages, which are templated, remember, can actually compare Git hashes to versions. That's because a Spack package might have if I'm at this version or greater, do something different than another version. And so we had to figure out a way to convert Git versions to that so that these templated packages would work. And when you put that all together, you're able to take a Spack environment and actually tie a pretty large code together in a way similar to what the Marble folks were doing before with their own sort of home build system. And so what you end up with is there's a list of specs up here. They have specific hashes for some things, and they have branches for others. They have package repositories down here that they pull from. I don't want to get too much into the details there, but basically we layer package repos. There's the mainline one that has the 6,000 packages that you saw. But there's some internal ones that are layered on top of that they can also use, where they have their own wrappers for internal packages that build on the external open source stuff. There's compilers down here, and then all of this is external configuration. So it's like all the stuff they didn't want to build that was already on the system. And it's a little long. I think we could probably pull this out into some included file, or it's basically generated with Spack external find. But now they can take this, put it in a repo, and we are working with them to try to improve this developer workflow to where they can use it day to day. And so we would like to get to a point where essentially if someone hands you a Spack environment, you can not only reproduce it, but you can also just pick pieces of it, work on them, and tweak them, and iterate. You're like a normal developer would, and have all of that integrated into one system. And so this is sort of what it looks like. You clone the map project, which is their sort of super project. You activate the environment. You say which packages you want to develop, and you get a directory structure like I showed before with the different components. One other handy thing about Spack is for these large graphs, you can actually srun Spack or srun Spack install. It does parallel builds, and so it'll coordinate through file system locks to build the thing bottom up and take advantage of the number of Slurm processes that you give it. We basically leverage the same mechanism for like a user running 2 instances of Spack to install 2 things themselves, and for parallel builds. So you don't really need MPI, you just need to run Spack. The whole thing generates a lock file like I described that would enable you to reproduce the environment. One question that comes up with the Marble team that we're sort of working on is, how do you manage lock files in a combinatorial build system, or where you're running across lots of different platforms? I think the systems like Ruby and NPM that inspired this were typically building things with like, where there really is only one version of a package. Ruby is an interpreted language, JavaScript is interpreted, and so like, if you just have the package and the version, and that's all you need to know to get that package on your machine. With HPC, it's like you need the full configuration of the thing, and the configuration is different on different machines. And so we can generate the log files for that. The question is just how to manage them, because we will probably have several different sort of canonical builds for the project that we need to deal with. And so maybe we can come up with a naming scheme or something that developers can set for that. So I mentioned that Spack environments are used for CI as well. And one kind of cool thing is that when you have this sort of build description of a code like Marble, you can take it and you can use that Spack CI command that I mentioned to generate GitLab pipelines for it. And so if you want to maintain builds of the whole system in CI as people submit them, you can do that, and we'll generate this pipeline here. We have recently expanded CI builds to basically build on every pull request. And so we're actually doing this in the cloud as well. So like if you submit a pull request to a Spack repo, we're managing the E4S stack and a few others internally. And if you modify something that touches them, basically we run every PR through this. We generate CI pipelines on a number of builder machines. And then you'll get this status update on your PR that says that everything built okay. And we're able to make that fast using build caches, but it still is a lot of rebuilds, because basically if you change something low down in the stack, the hashes above it change. And so that's we're working on that. You can look at stats if you want to, stats.e4s.io, and we're doing about 100,000 builds a month on all the pull requests that come into the Spack project right now. And we're trying to reduce the number of failures that we get and handle all the infrastructure issues that come with that. But it has been super helpful with vetting releases and making sure that we've caught a bunch of bugs that would have broken a lot of packages using this. And so we're trying to expand it and to have sort of an optimized binary release of Spack eventually available for different architectures. That's been our goal for a long time, and it's actually taken a lot of effort to scale this thing up to the point where we could think about it. And so if you think about Spack as like a distribution system, this is your traditional OS package manager. You might have a recipe for per configuration. You throw those in the build farm and you get portable binaries out, and you have one stack that gets upgraded over time in place. With Spack, what we're really trying to do is you have parameterized package recipes, so fewer recipes. You throw that in a build farm, you get more different binaries that are optimized for different platforms, and you might have many different stacks for different platforms. So you could think of it as both, a package manager to wrap your build system, a distribution system, and sort of a way to generate different distributions of software. And if you think about how HPC works and what staff at HPC centers really do, they are iterating on a stack of software, right? They're all building their own little tiny distro for their site that they maintain over time for users. And so we're trying to sort of unify those ideas. And then, as I mentioned, like users can always build directly from source as well. So we're really trying to seamlessly combine the source and binary side of things. I probably don't have time to get into details of Spack here, but this just came out. We have improved sort of the core concretizer in Spack quite a bit, and that's sort of we've made that the default in the latest release. That's our first C++ dependency, and we've always wanted people to be able to run Spack straight out of the Git repo. And so we added binary bootstrapping, where we can basically download a binary package out of the box and run the solver that way, so that we can actually have the concretizer work. We've added some stuff to address problems people have had with Spack in the past. And so probably the biggest one is this install -- reuse thing. Basically, because we hash the graph, and the way that we were reusing built packages is we would try to find a match for a particular hash. We would get a lot of misses for relatively small changes. And so, like, if you used Spack for a long time and continued pulling from develop, and you installed something again, you would get sort of a new build with the latest settings of that thing. And so people would have like 3 Pythons installed. There's a new reuse option on Spack where we can try very hard to reuse things that are installed. And so I'm going to skip through all this concretizer stuff, but this is the difference with 0.17. If you do the old solver, right, and this is more details than you would normally see. I'm just showing the stats on how we prefer different packages. If you built HDF5 with a bunch of packages installed, it may actually miss all of them. And so it doesn't actually reuse any of these things because it generates hashes that aren't installed, and it looks to see if that hash exists, and if it doesn't, it has to rebuild it. With the new concretizer, you can run the same command, and basically it says, oh, well, all of this stuff, I can use the versions of these things that are already installed. And so it does this optimization in addition to the solve to try to pull in dependencies and make sure that they work with your stack. And so here, we're only having to build 4 packages to get HDF5 working, whereas if we use the hash matching scheme, we would have to build 20. So I think this is probably our most wanted feature, at least our survey said that it was. If you look at our survey from a year ago, the top thing that was asked for was this sort of reuse of existing installs. And so in 0.17, we've got actually reuse of existing installs. It's actually done now, and in the release. We've gotten all of these different things done: the better dev support, the new concretizer, reuse, CI, and package testing. And we've actually got the first PR up for Windows support for Spack as well. So we're trying to expand there. So that's it. I think, if you're interested in getting involved, it's pretty easy. There's you can submit a PR to the Spack repo for packages, or if you have some recipes that you built during the hackathon, feel free to submit pull requests to Spack. And we'd love to have more contributions. So yeah, any questions?
So
Good question.
If no one asks, so I would just want to say 2 things. First of all, I would like to personally thank you for this utility, because from the first time I saw it, I fell in love with it.
Thanks.
And the second thing, this is just the comment. Yes, this reusability feature is really, really useful, because a few months ago, I actually bought a new SSD disk just to mount to opt, where is my spec, just to fulfill the disk usage, because it was like using all opts that they had. So yeah.
Awesome.
Okay, thank you.
Thanks.
maybe one quick question. So since you combine all of the different versions or continue to add the different versions to the recipes, I was wondering whether they get then very complicated over time. And I was also wondering to which degree then all of these different combinations of versions and variants are all tested, because I guess this kind of combinatorially explodes.
Yeah, it does. So that's why we have the CI for where we test particular stacks. I can show you some packages here. Let me open something up here. Let's get rid of this. And like if you look at LLVM, right, which is one of the more complicated packages, it gets to be pretty large. And here's the LLVM package. Here's all the versions of it that are installed.
Sorry, we're still seeing your
here, let me okay, good. I'll share the screen again. So can you see this?
Yeah, now we can.
Here's the LLVM package.
Mm-hmm.
And it has a bunch of versions in it, so we get this block of hashes. Mm-hmm. Lots of different variants in it, and yeah, the build logic is pretty complicated. But I guess
I can imagine.
I would say one nice thing about it is that it really does reduce duplication, and it sort of I think I originally struggled with this because when we designed this thing, I think most package managers were doing sort of the same build but tweaked slightly for different versions. And you get reproducibility out of that, but you don't really get reuse of the build logic. And the design point that we're kind of going for in Spack is in HPC, you port to new machines a lot, right? Like you end up trying to run new scenarios frequently. And I think I found it really hard to reuse anything in someone else's build recipe. And so when you force people to, update the packages, I think it can get complicated to figure out how best to update the package, right? And we have to have testing to make sure that they continue to work. But
obviously,
but you do get a lot more reuse out of, I think, the logic in them. And so for the testing part, let me stop this share and do another. If I go over here to say, I'm going to share again in a minute. Let's see if I can find that right. Yeah, I'll just. So if I share this here, can you see this? This is just a Spack repo on GitHub. If we haven't really probably documented this as well as we could, but we're increasing the number of stacks that we actually test. And so like we have some stacks that test the different build systems. We have a DataViz SDK that has like PowerView and stuff in it. There's an E4S on Power, E4S on x86. There's a Radius stack. This is a Livermore thing. And then we're trying to put the whole Spack tutorial in here. Essentially, all of this stuff is getting built on every PR, or at least the parts that are changed. And so we're able to maintain that configuration here. And so, this is the granularity that we are currently testing the packages on a regular basis at. And I guess, yeah, it's true. It's easy to make something with Spack that you haven't built before, which is both a strength and a weakness, right? And I guess the thing I would like to have is, so with this new concretizer that I didn't get too much into the details of, but if you think about what it's doing when it's reusing packages, it's looking at what you have installed or what's in a build cache and trying to pull from there. I think we could take these tested stacks and sort of flesh out dimensions of the ecosystem and say, like, here's a particular CUDA stack, here's the Rockwell stack, and so on, and use them as kind of baselines. And basically, we could tweak the optimizations in the solver for the stuff that is in the baseline.
It's tested.
But if the user asked to do something slightly different, yeah, that's right. So basically build a mostly tested graph that reproduces the baseline, except for what the user wanted different, and then let them change one thing at a time scientifically.
I see that, and it sounds like a good idea. Another quick question I had is just became, because it also, of course, came from Guix. So now I guess in the recipes you specify where to download the source. Yeah. And I was wondering if there's any kind of protection against that source disappearing at some point or something like that, or if that happens, one has to update or find some other repository to download from.
We actually have a mirror in a CDN for all of Spack. So like if you look in the default Spack configuration, there's mirror.spack.io. And we, for any source file that gets checked into Spack, we upload it to the mirror so that if it goes away, we'll still have it. And also it's good for redundancy. So if the site goes down, then you'll still have the files. So yeah, you may not have noticed, but if you're yeah, we have an S3 bucket that has everything in it, and we put it out in CloudFront in AWS.
So this means, let's say some simulation code is being built and the Spack recipe downloads the source code. That source code of the package gets put into that S3 bucket.
Not your private one, right?
Okay.
Like if someone checks something into the public Spack repo, then we will go and take all the tarballs out of that and stick them into Mirror.
Okay.
But if you use Spack at your site, we don't upload your local data.
Okay, no, I wasn't worried about that. Okay, cheers. Lionel has a question as well.
There we go. I thought I was plugged in, but the hotel lamp apparently is not powered. So there, I'm good now. Okay, sorry, what's the question?
Yes, it's a naive question because I know very little about package management. So how deep goes the dependency stack? It goes down to the Linux kernel. Is that it?
No, not that far. So Spack actually doesn't. It goes down pretty much to the compilers and their runtime libraries right now. And so you build something with a compiler. It probably uses the system libc, and we're actually working on that. We would like to be able to swap out libcs in the way that like Nix and Guix can do. And it uses the compiler's runtime libraries, although it does RPath the compiler for you. So it says like, okay, we've had all kinds of problems with modern C++ versions having incompatible libstd C++ libraries. And so when we build with a particular compiler, we go and RPath the runtime libs. But outside of that, unless you specify externals yourself, you really shouldn't be pulling stuff in from the external environment. There are a few like base dependencies currently, like make and patch, that I'd really like to have Spack bootstrap itself. But aside from that, it's pretty much building its own stuff, unless you tell it to build something else or to use something else.
Okay, thank you.
And I mean, its own stuff can be a lot of stuff. Other folks? Anybody?
Yeah, if I may.
Sure.
Hi. Yeah, so thank you very much for it's a great tool. I have a question which is a bit like I noticed that you're quite interlinked with Amazon. So you mentioned that you store something on S3 servers.
Yeah, that's right.
So I can imagine that as you continue, there will be more and more packages, and so you will probably require more and more computing resources to deploy, to test, to store things.
Yeah, that's right.
So what's the plan for the future? I mean, like this thing will probably require quite a lot of funding and support.
Yeah, so we have, we're working out, I mean, Amazon has actually provided us with quite a bit of cloud cycle time already, which is nice. I don't know if you noticed that they started using Spack in Parallelster and stuff like that. They've been supporting the build farm that I mentioned, and that's been really nice. And I don't know, they seem to just, they use it themselves, and so they want to contribute to the open source project. So they're also, paying for the CDN and the CloudFront stuff and the GitLab servers, basically all the services that we run in the cloud at the moment. So, I guess we'll use that while it lasts. There is like a sustainability question around, what if Amazon decides that they don't want to pay for this anymore? But I'd say DOE is large, and like the Spack currently, at least for the developers on the core team, we have funding from the ASC program, which is one of the big DOE programs. It's what does the simulation codes for the NNSA labs, and from ECP, which is sort of, I guess, half and half for the developer effort right now. ECP will end in 23, but I don't know if you saw that there's a bunch of discussion right now around sustainability efforts in the US for scientific software. So like if you, I could send a link maybe after this, but there's a RFI, which is like request for input, from the Office of Science right now for, you know, how can we sustain this stack? And I think what's expected is that there will be some software sustainability program that comes out of DOE, but we don't know. So, you know, we're working on it. If we don't have that side of DOE, we will have the ASC program because the codes rely on it. And so at the very least, we'll be able to sustain it that way. And I think, you know, if ASC can sustain this kind of thing, I think they see it as valuable and will continue to pay for it. So we have options. But yeah, that's the complicated part of running a large project. It's figuring out how to keep it going.
If other people don't have more questions, I have also some more maybe. So yeah. One is, so if I understand correctly, the Spack repository is still kind of centrally managed. So all of the recipes are kind of collected there. And I was wondering a bit about your thought process versus other tools, which kind of then go to have all of these feedstocks in individual recipes.
So I like the Conda model in that, like, it seems it's cool that you can set up a feedstock and that you can have like free CI and take advantage of the fact that GitHub Actions gives different repos, you know, their own time allocation. I guess that was never really going to work for us because, at least, I don't know how Conda does it, honestly, like for things like LLVM that take forever to build. We have our own cycles because we want to build for fancy architectures and we want to build optimized, and we don't get the kind of guarantees out of like GitHub Actions of builder architecture that we do out of, you know, where we can say what kind of instance we want or where we can run on a particular Livermore machine. So, I mean, that's part of why it's centralized. I guess the other reason is that the Spack CI stuff I showed is leveraged with what ECP is doing. When we set out on that effort like 4 years ago, we wanted to build something that could work. I mean, my motivation was to get something that would work in the cloud for Spack, but also something that could be used internally at an HPC site. So we made we worked with GitLab, and have you seen Yakimar CI? Basically there was an effort under ECP. So yeah, you can go to ecpci.gitlab.io. And this is a runner for GitLab that will securely run user jobs within the facility. So if you submit to your local GitLab, it knows your user ID and it runs your CI job as you or as a user that you can SU to on the cluster. So with this, basically, we were encouraging HPC centers to use GitLab. And so we used GitLab behind the scenes to sort of have uniform CI. So we can take CI from the cloud and we can run a similar pipeline internally. There's no reason that Spack CI couldn't have another backend. In fact, like Vanessa Socket is at Livermore now, and she's sort of keen on getting like a SnakeMake backend or a GitHub Actions backend for it working. And so I'd like to see that. I don't think we need to be tied to GitLab. There was one other thing I was going to show. There is another project that you might be interested in. Yeah, it's called Radius CI. So RADIUSS CI. So Livermore has this. I'll send all these links out afterwards. There's a project called Radius at Livermore to sustain a certain set of open source projects. And so basically these are core packages that our codes use that we want to promote as sort of a software stack for other folks to use, both outside and inside the lab. And so this project, it's called Radius, which sort of means nothing other than that's the project. They made a tool that lets you very easily set up project CI using Spack. And so you can mirror a GitHub repo internally on GitLab, build on your own machines with it, and so on. And so that's what this is. So things are being built on top of it, which is pretty cool. On the repo thing, so you asked about like centralized repos. We want to have a good central repo for Spack so that it works like a normal package manager, and you can just say Spack install something, and the typical user doesn't have to pick, you know, the stack they want. We give them a good default. But you can set up your own internal repository for Spack too, and some sites do. Like, so I've seen some projects set up their own Spack repo that builds on top of the built-in one. and teams internally will set up repos for their own projects too. So
since you're coming to speak on
there's nothing.
Sorry, yeah.
No, go ahead.
About the binary, the public binary catalog that you mentioned. So maybe just a practical question. So let's say if I were to use Spack to, let's say, locally on my MacBook or something like that to install PyTorch versus using Pip or using Conda, what are currently the kind of, so how likely am I to have to compile a lot of stuff, or will it just pull stuff from the binary cache and everything will be done?
You're very likely to have to build stuff right now because we haven't made the binary cache public.
Okay.
With the reuse thing, basically, like we have a binary cache that our CI uses, right, for a certain set of packages, and it's pulling on every PR from that binary cache, and it gets a pretty high hit rate. With the reuse feature, you should be able to expect that you would pull the typical build from the binary cache, and you wouldn't have to build much of anything. I mean, that was one of the points of it, was that, like the Mvapich folks have been trying to distribute Mvapich as a binary through Spack for a while, and it's been kind of clunky because you had to check out the exact revision of Spack. You had to set things up like their environment, and you had to register their repo. And then you would get the hash matches with what they had. But basically it was on the user to generate the right hashes, which seems like too much. So with this thing, you would register the repo, say install that thing, and it would pull from the repo. And I think we'll have some more CLI to make that more specific, so that if you want to say like the binary with this hash from that repo or something very specific like that, you could do it. That's not in there yet.
I see. Just to understand. So you were talking also about this E4S binary cache, right? Where you said, okay, so this one is not public. It's just
that one is public. So that one
is public. Okay.
Yeah, that one is public. So you can use the E4S binary cache right now. It's just that we don't have one for Spack mainline. But the E4S cache is, that's maintained by the E4S team, and they do have workflows that are building on that.
Okay, but is there a reason not to use that one, or?
Nope. It's the only reason would be it's not everything in Spack, but I mean, it's the only binary cache out there right now. So you can definitely try it, right? It's like 400 or 500 packages out of the total. And so it's...
Okay. No, I understand. Okay.
E4S is sort of, it's a project under ECP that maintains the stuff that ECP is interested in. And so,
because your slide said the E4S team has this binary cache with 50,000 Spack packages. So I was wondering what the
50,000 builds of the 500 packages that are in E4S.
Okay. Okay, now I understand. Okay, cheers. Thanks a lot.
The combinatorial thing, yeah.
So I have a question about the design of Spack, because if you want to make a new package for Spack, then you have to make a pull request of the repository that contains the sources of Spack, and you have also the list of recipes of packages in the same repo. So is there, do you have some motivations to do it like this, or it was just for historical reasons?
Spack started as it was based on both Nix and Homebrew, and that's how Homebrew was structured at the time. So it's partially because of that, just because of inertia, and partially because right now we don't have a stable package API, and we don't really have a great way to manage to sync the version of Spack with the repo. I mean, we could fetch a version of the repo, right? I would like to have a better metadata in the repository itself to indicate sort of what Spack version you need to support the packages in the repo, and we don't have that right now. And I think development has been going really fast, and so we're changing rapidly, and so we've just kept them coupled. But I think if once we go 1.0 or whatever, I think we would have a stable package API and try to pull them out, because I think it makes a lot of sense.
Okay. Thanks. Yeah.
How far away is 1.2?
The last thing that I have wanted to get done for that is like this repo metadata, and we want to rework the way that compilers are done in Spack. And I didn't get to that in the presentation today, but if you notice in Spack, the compilers are kind of they're an attribute on the node in the graph. And so it says like this node was built with GCC at a version. But there's a lot more to compilers than just the name and the version. And so we have this sort of very primitive dependency mechanism for compiler right now. And what we have to do for El Capitan, the machine that's coming to Livermore in like 2023, is we really want to support compiler interop better, where you could mix compilers and have like the AMD compiler, the Cray compiler, and GCC all in the same build, with you know, get the right OpenMP implementation that supports all of them. We are trying to model the compilers at a deeper level, so basically the compilers will become build dependencies, and they will add link dependencies to the things that they build. So we can model the runtime libraries. And that'll help us basically combine compilers. It'll help us avoid libstd C++ errors. It'll help with compiler bootstrapping. So if you want to build with a compiler and you don't happen to have it installed, then we'll just install it for you. But there's a fair amount of refactoring that's going to have to happen for that. I'd say we have the machinery in place right now with like, so Spack compiler find and Spack external find are doing similar things, right? One of them is finding compilers and adding them to compilers.yaml, and one of them is finding packages and adding that to packages.yaml. And so, you know, I think we will convert compilers to be packages. Compiler find will become some, you know, special case of external find, and we'll get rid of compilers.yaml and all of that configuration. And basically compilers will be externals like anything else. Once that's done, and we have a public binary cache, I think we could start talking about going 1 point, but I think that's a major change still that I think will be somewhat disappointing, you know, support for everything just yet. Although, I mean, you know, the people do use and rely on Spack a lot already, and I think, you know, we would continue to try to support them and make it a smooth transition.
As someone who has never used EasyBuild, I was wondering kind of what is the kind of the differentiation with respect to EasyBuild or the similarities?
Here, let's go over here. I'll show you. So if you think about how this is actually the difference between Spack and Nix as well. Spack has dependency resolution, right? So when you have a templated package that has version ranges and things like that in it, and you take this abstract graph, you concretize it, and you store that, and this is your reproducible build, right? If you think about the way that EasyBuild packages work, you're doing the concretization by hand. The graph is solved by humans, and in Spack, you're solving it with a solver, right, with this concretizer. And so EasyBuild doesn't have version ranges, and you have to do different easy configs for different versions of packages, right? They have some nice factoring between like the easy block with the fundamental build stuff and the sort of smaller configuration details in an easy config, but humans still have to write that stuff. And so like porting a stack involves like replicating hundreds of easy config files, whereas in Spack, we're trying to minimize that effort, right? It's the reuse of existing build logic, and we hope that the existing packages can, you know, eventually converge and be able to build pretty well anywhere.
Yes.
That help. That's my view of the difference. And so, I mean, you know, Kenneth would tell you that EasyBuild is more reproducible because you write the recipe by hand and so on. I would tell you that there's a lock file and you can reproduce that if you want to, and we help you as well. And so you can have the best of both worlds, but it's your call. Try them both.